Welcome to everybody for this fourth lectures. We have changed meanwhile the book, as you can see on the shared screen of Maurizio. It's again the same author, but it's the third volume of this series, which is entitled Differential Geometry. And we are really excited about this lecture. And thank you again, Maurizio, for these classes.
Okay. Thank you, Roberto, for this introduction. Okay, this is the first slide. So we are starting with a new book. This new book is about differential geometry, and I underline, sorry, change of pen, and I underline the word geometry. That means finally we are doing some geometry, because geometry means we are measuring things. And since the first lecture up to last lecture, you should have probably noticed, or at least I remarked, that we haven't done any measure. I mean, we were just technically doing something which is called differential topology. So the topic of this lecture is the geometry. Okay. This book is very recent, I think from 2017, so modern book, a modern point of view, but it is very well written as the other one and also the first one, and I strongly suggest you buy it and you study it. Okay, go to page 6, let's follow this suggestion. As usual, we have highlighted, I have highlighted in these notes the part that for the lecture we will look at, but of course, when you are studying the book, I strongly invite you to read everything. So, as I already said, up to now we were doing something which is called differential topology, meaning the shape in the sense, not the shape, just differential topology of the spaces, the differentiable manifolds without a metric in it. Now we are doing geometry with a metric. A metric is a way of measuring length of vectors. And as you know from the scalar product in Rn, length of vectors means also distances, angles between them, the notion of area, volume, curvature, to be or not to be straight as a line, and so on, and minimal connecting paths which are called geodesics in differential geometry, and so on. And this is what distinguishes geometry from topology. Okay, actually, there is another concept very important. What I'm telling you now is this, the metric part, the metric aspect of geometry. Actually, in particular for the notion of curvature, when you want to measure how much a space something is curved, one way to measure this is to take derivatives of the vectors on this space to measure how much the derivative is changing, how much the vector is changing on the surface. And this means taking the derivative of this vector with respect to a certain direction on the surface. Okay, so taking these derivatives, in some sense that we will make it more explicit in this lecture, is the notion of connecting two different tangent spaces between them. Because when I'm measuring how much this vector, a vector on the surface is changing with respect to the same vector but on another point in the surface, I need a way of connecting the two tangent spaces. Otherwise, I cannot compare them. And so geometry, another point of view, is made by the notion of a connection, which is in some sense an alternative to the metric. What I mean is that you can make differential geometry using a metric or using a connection, a slightly more general point of view. The good news is that when you have a metric, which is the most natural way of looking at geometry, then there is a unique, very, very good connection on the space. And so the 2 point of views from this point of view, the two notions coincide in this case. Okay, enough for this. So I told you that we need, as the first thing, we need to measure how much tangent vectors are changing, or more general, normal vectors are changing on a surface in R3. This means taking derivatives. And so we will start with directional derivatives that I hope you already know, because it was the main topic in the first 3 lectures. And after that, we will talk about connection and curvature from this point of view. After that, there is a very big jump to a very theoretical point of view, very useful, which is the one of connection on principal bundles, but we will reserve it to the next course next year, or in few months, if you like the idea. Then go to 18. So already 18 pages done. With this rate, we can finish the book in half an hour, okay? So let's start with the first section. First, to understand this book, it would be helpful to have had some prior exposure to the theory of manifolds. You had it in the first 12 hours of course. Just in case you haven't started yet studying this topic, here very good news. This book is trying to be as much self-contained as it can be. And this means in particular that you have a beautiful appendix where this appendix, you can find all the material from the first 12 hours, the material that is needed in this part of the course. So if you haven't started yet studying the other book, for the moment, skip it and just look at this part of this book. Okay. So we have geometry instead of topology. Again, this sentence, we already know this. But in a single example, can we understand what this means really, geometry instead of topology? Well, look at the, I don't know in English, geographical map. I mean, a map of the surface of the Earth. And then you would agree that a very good map should show distances which are accurate, meaning that distances are proportional. But you know, it is not the case on a map. The problem of the Mercatore map is the fact that distances are vastly distorted around the poles. Okay. Well, the question is, could it be possible to write a map on a piece of paper that show distances exactly in scale with the true distances? Well, it happens that it isn't. And the reason for this is the fact that the sphere is a curved space, and the piece of paper, the sheet of paper, is not a curved space. So the aim of this lecture is to understand deeply, in as much as deep as we can, this notion of what does it mean a curved space. From this point of view, well, let's say this later. No, okay, I can tell you this right now. Let me check if I can use the camera. I'm disabling the screen sharing because I need the camera. Okay, so now you can see me. This is a cable, okay, the mouse cable, actually. Can you confirm that you can see this?
Yes, we can. Yes, we can.
Yes.
And can you answer this question? Would you call this cable curved or not in the space?
Probably yes.
Probably yes. Very, very good. But look, I'm now showing you that without changing distances between points in the cable, I can change your answer. Is this cable curved or not?
Not anymore.
Not anymore, but do you agree that I haven't changed distances between points on the line, on the curve?
On the curve, yes.
Okay, so from the point of view of a person living on this cable, just like in Flatlandia, and having nothing more, having no perception of the outer space, nothing has changed. Okay, the distances haven't changed. So from his point of view, from this intrinsic point of view, for him, this cable is not curved. Okay, can you understand at least qualitatively this argument? Okay, I just showed you, this is just a proof, very non-mathematical proof, that every curve is isometric locally to the straight line. So for the curve, there is no intrinsic notion of curvature. Okay, but anyway, I agree with you that there must be some notion with respect to which this cable is curved. From what we have said, the important part of this, of what I'm saying, is the fact that this cable is curved into the space. It's curved with respect to this shape, the way it is embedded, it is put into the space. And in fact, Roberto, you were saying that distances are not changing, but maybe you want to add something. Actually, distances from a certain point of view are changing. If we are measuring distances, where?
It depends on the point of view. In this case, in the space in which the curve is embedded.
Exactly. So from this point of view, distances are changing. So for a person living in the space, which is more common than living on a mouse cable, actually, this cable is curved, okay? And we will call this notion extrinsic curvature, while 0 is the intrinsic curvature of the cable. And from what I'm saying, extrinsic curvature is not a property of the cable, but it's a property of the cable and how this is embedded in R3. So it is a property of the map from the real numbers representing the abstract cable to R3. Okay? Mm-hmm. And this makes completely two different points of view in differential geometry: the extrinsic point of view, the extrinsic geometry, and the intrinsic geometry. And so we are now, all the lecture will be permeated with this difference. Sometimes I will tell you, okay, this is an extrinsic notion, this is an intrinsic notion, meaning that this depends on the embedding, and this other notion does not depend on the embedding. As you can imagine, extrinsic curvature, the extrinsic notion of geometry came before the intrinsic notion of curvature. And as you can imagine, we mathematicians, we like very much intrinsic notions, because they are absolute. So the object describing the intrinsic curvature of a manifold will be, well, I'm spoiling all the lecture actually, but let's say this, will be the famous Riemann curvature tensor. As a tensor, you can imagine, it is not a single number. The Riemann curvature, the only notion, the intrinsic notion of curvature for a manifold is something which depends on 4 dimensions. Is a tensor of rank 4, is a tensor of type 3-1. Okay, meaning that you need a lot of numbers, 4 times infinite numbers to describe this, a 4-dimensional space of numbers for describing the way a space is curved. I think this is fascinating. I mean, you cannot say a space is curved 3, a space is curved 4 or -2. Okay, in order to completely describe the curvature, you need several numbers. Okay, 4 numbers, I mean 4, dimension 4. Okay, so the lecture is almost over. I said everything we need, and now we just talk about details, okay? From now on, just details. First of all, the definition of a metric. Now, allow me to assume that you already know what is an inner product on a vector space. But, of course, we need to establish some notation. So I will go through this section just to focus on the notation, the terminology, and so on, okay? But I don't expect that you do not know this part. In particular, this is a vector. As you can see, we put vectors in vertical. This is common for mathematicians. And we focus on R3. But please don't stop thinking to everything, if you can, if it doesn't bother you, as done on Rn. Okay, the peculiarity of this book that it is focused on letting you visualize and understand things, which is, it's very nice, but don't lose the focus, the fact that we are doing geometry in n-dimensional space. And by the way, we are embedded in Rn. For what I was telling you, for the moment we are considering manifolds, you know what a manifold is now, which are embedded. That means you can consider these manifolds as a subset of a certain space Rn. Okay. Before doing that, remember that on Rn, on R3, you have a scalar product, which is a distance, right? The scalar product, take the scalar product of the vector with himself, and you obtain the length of the vector to the power of 2. That is this part. You know, you can define also angles, and more, very important, you can define the length of a curve in the space. Okay, this is the tangent vector to the curve. You take its length, and you see that now we need the length. This is a tangent vector. Remember from the first hours, from the first part of the course, that the derivative of a tangent the derivative of the curve is a vector, but living in the tangent space to that curve. Okay, so we can take the length of this tangent vector, because we will see in a few slides, in a few pages, that this length is defined on the tangent space and not on R3. And you can integrate it, and this is a good notion of length of the curve. This means, in particular, that you can parameterize the curve with its length. And I assume you already know what I'm talking about, meaning that we are running on the curve at the same speed as the tangent vector. In this way, the tangent vector will have length 1. Okay. Now, since we are mathematicians, we like to take out the properties, in this case, the inner properties of the object we are talking about. In this case, the inner properties of an inner product are these 3: positive definiteness, symmetry, and bilinearity. Okay, so we say that this is any bilinear form satisfying this property is an inner product, is a metric. Okay, and you know what? This is very important, trivial, but very important. If you have an inner product, a notional length on R3, but then you take a subspace in R3, a plane, then you can put an inner product on the plane just as the restriction of this inner product. In concrete terms, in terms of manifolds, means that when now I will put a manifold inside Rn, since there is a metric in Rn, then we have automagically on every tangent space to M, which is a plane, which is contained in Rn, in a certain dimensional plane contained in Rn, we will have a metric. Okay, so I will implicitly say, okay, let M be a submanifold of Rn, and I will mean and take the metric induced on M from Rn. Okay. Now, of course, since the metric is a bilinear form, it means that once you choose a basis for the vector space, you can represent this product between two vectors by matrix multiplication. And the standard formula is this one. You see? I think it's a formula that you already know. I mean, if the matrix is representing a linear map, you just take the matrix times the vector and you obtain a vector. But since this matrix is representing a bilinear map, then you need to apply the result, the vector, again to the other vector. And the property is this. If you want to compute your bilinear map, the real number that you obtain on certain two vectors, you just take this multiplication. Is this formula clear? Everybody knows?
Yes.
Okay. Well, what I'm saying from a more global point of view is this. Okay, the scalar products on a vector space are in bijective correspondence with symmetric matrices which are positive definite. And I'm saying here, this relation is not canonical. Why? What does it mean? Can you answer this question? Why? What does it mean not canonical?
Depends on the reference system.
The basis. Perfect. We had the answer from here, from the classroom, that meaning that it's not canonical. It means that this map depends on the chosen basis. Okay, I'm stressing this terminology because we mathematicians, we use it very much. So if you want to learn how to read the book written by mathematicians, you have to become used to this kind of terminology. If you listen to the other lectures, I already stressed out very much this kind of terminology. And remember a very abstract notion about the tensor product between multilinear maps. If you think about it, now this means that a scalar product is just the tensor product between the dual basis of a certain frame. And I have put this as an exercise when you will study by yourself. Try to do this exercise, that is, explain why this notation works, what does it mean. But for the moment, just remember that this is the mathematical synthetic way of describing any metric on a vector space. Actually, this is just any bilinear form, and the fact that it is symmetric is given by the symmetry of the coefficients, and the fact that it is positive definite is given by the fact that this metric is positive definite. Okay, so finally we have the definition we were looking for. That is, what is a Riemannian metric? Well, a Riemannian metric is just what I'm saying on a vector space given on each tangent space. Okay, so this is important. The Riemannian manifold, the Riemannian metric, Riemann is the person who first thought about this abstract notion. It is just a scalar product on every tangent space. Okay, nothing more. So don't be scared, because if you get scared now just by the definition, then we are over with the lecture. Okay, so please try to get used to the fact that we are talking about a manifold that on every tangent space possesses a scalar product. Okay, this scalar product is called Riemannian metric, and as usual, this scalar product, this is the scalar product, right? But it's a scalar product on the tangent space, and we have several tangent spaces. So I should put a point here. And this is a scalar product, so I can say a bilinear map, symmetric, maybe I can say symmetric on the tangent space. Okay, so you see, it's very easy to make a cumbersome notation, very ununderstandable, but the concept is very nice. If I want to make things more difficult, I can say that this, because I'm not putting a point, this is a section, remember from the first part of the course, is a section of endomorphism of symmetric bilinear maps. Sorry, need more space. I could say this, that this is a section of symmetric tensors on the tangent bundle. 1, 2, 3. Okay, what I'm saying is that don't be scared if you, at a certain point, you have a definition like this. Nothing to be scared of. Now you have the tools to understand this definition. Section means just that you can remove section if you put the point here. Okay, and in this case, it means that the thing that you have is something on the tangent space in that point. This is the only meaning of section, okay? It's a very natural notion, but means this. And this is something we are used now. We have the tangent space, we have something that we can do on a vector space in general, and we do that on the tangent space. And we ask ourselves, is this useful to study the manifold? Okay, in this case, it is very useful. So, starting from now, we have a metric on Rn, and this metric is the standard metric. But from what I'm telling you, you should already understand that the metric on Rn I'm talking about now is not the metric that you know, because the metric that you know is just the metric on Rn in one single point, the origin. When I say the Riemannian metric on Rn, I mean that very same metric, but on every tangent space on Rn. So it is not just one metric, but it's a copy of the same metric translated in every point. This is very important, in my opinion, to think about this distinction. The fact that they are absolutely the same, because of course just a translation is changing nothing from no point of view. This is the origin of the fact of the several confusion that there are when a non-mathematician is doing differential geometry. Because in Rn, everything is obscured in some sense by the fact that Rn is too simple and everything is the same in every point. It is homogeneous from several points of view. Okay? So, with this new point of view in mind, let's go on. This means in particular that if we have a surface in R3, then this surface has a Riemannian metric. Why? Can you tell me why, referring to something I said a few pages before? Why, if I have a surface in R3?
Some manifolds of R3 is R2.
So we have said before that exactly. That if you have a scalar product, this is a scalar product also a subspace. Exactly. So any surface in R3, it's a Riemannian manifold. And not only a surface in R3, but any regular submanifold in a Riemannian manifold. Why? Not only surfaces, because for the same reason. If we have a scalar product on the bigger space, on the ambient space, this scalar product gives a scalar product on the submanifold. Very, very good. And of course, remember in the first part of the course, we were interested in diffeomorphism, that are maps between two manifolds which are differentiable and invertible, right? Now we have something more on the manifold. On the tangent space, we have a scalar product. So it makes sense to look for maps that preserve not only the differentiable structure, that is diffeomorphism, but also for maps that are preserving the scalar product. These kind of maps are called metric preserving, or when invertible, when diffeomorphism, are called isometries. Okay, so you probably already call isometry something between vector spaces, which is something which is preserving the metric on the vector space. But the metric on Rn, the metric on the vector space, is just one metric in one point in the origin. Okay, this is the same notion, but since we have several metrics in several tangent spaces, we are requiring that this induced map between tangent spaces, we know what this is from the other part of the course, is preserving the metric in this way. Okay. Yeah, there are examples, and I want to show you this example about the torus in R3. You probably know this submanifold of R3. It's the donut. Okay, it's called a torus, and this is the shape you see of the torus when this is embedded in R3. Would you say that this space is curved or not? Same question as before. Just we are no more using a thread, a cable. We are just using the donut. Would you say that the donut is curved in R3?
Yes.
Okay. So the answer now is yes and not. It depends on which point of view. Well, the answer is actually surprisingly the same as the cable. Is no, it isn't curved from an intrinsic point of view. Yes, it is curved as a submanifold of R3. How can we prove that this isn't curved as a submanifold? This isn't curved from an intrinsic point of view. How can you prove? You can prove in this way. You can take a metric which is clearly not curved on the same space in this way. Take a piece of paper, this one. Let me switch on the camera. So this is a piece of paper, okay? And I'm now taking the identification of two sides. I'm making a cylinder this way. Okay, this is a tube, a cylinder. Can you imagine now that I can curve this cylinder and I can make a donut? Of course, I cannot do this with a piece of paper because I'm trying to transform this piece of paper into the embedded torus in R3, because this transformation is making an embedding. But you can imagine that we can actually do this. And maybe with a piece of paper is not clear, it is more clear this way. We can do this in this way. These arrows means that you should identify the opposite sides in this direction. Okay? So from here, you obtain a torus from the differential geometry point of view. This torus, you can put on it a metric, which is this metric. I mean, this is an induced metric, no? From this point of view, because it is the same metric you have on the piece of paper. This kind of torus is called the flat torus, and this kind of torus is flat, of course. Well, it's not clear. Later we will make some computation on this kind of submanifold of R3. Okay. So my mistake, I mean, this is flat, has no intrinsic geometry, but this has an intrinsic curvature, okay, the other space. So the answer that this is curved is correct, actually. Okay, so important thing, do Riemannian metrics exist on a manifold? Answer, yes. Let's go on. Every manifold admits a Riemannian metric, okay? So we are not talking of a useless concept. And just to give you an example of a not trivial metric, actually a very, very important metric, just this one. Think about the upper half plane in R square, okay? That means the y coordinate is greater than 0. Here we have the standard scalar product, okay, as usual. And as usual in tangent planes, not just on a single point. And of course, we can take any multiple of this scalar product. For instance, we can take this scalar product times 3. We still have a scalar product. We can take this scalar product times 1 over y squared, where this number depends on the point we are considering the product. Okay, so as high is this point in terms of y coordinate, as small is the scalar product between two apparently equal vectors. Apparently means using the identification of vectors that we have in R square, which is confusing and hindering several notions. In this case, is hindering the notion of the fact that this vector, as much as it gets high as a level, it becomes shorter. Okay, from this metric point of view, with this metric. This is a very important metric because this is a model, very nice model, we will see at the end maybe, of non-Euclidean geometry. Okay, it is called the hyperbolic plane. In this plane, there are examples. If you take a line, a straight line in this plane, and the point which is not on this line, do you know how many parallel lines to the first one there are passing through that point? You know that in Euclidean geometry, the answer is 1. In this geometry, the answer is infinite. Surprising. Okay, we will see at the end, maybe. Okay, then let's talk about curves. Now, we have curves in Rn. We already talked about them. Maybe remember. Okay, this is an example of curve. This is the map. Okay, meaning a curve is a map from an open subspace of R. You can take the whole R, or you can take a -1 plus 1, and so on. You can also take a closed interval, A, B, and usually we take this, meaning that the curve is any smooth map between a little less than A and a little bit more than B to R square, R3, R4, and so on. Okay, I'm talking about this. This is a curve. This is a way, the trick we use so that we can talk about the value of the curve, the end points of the curve. Sometimes we need the end points. Okay, so we take the image of a closed interval, but we always assume that the curve is defined on an open interval, a little bit bigger. Okay, and the curve has no intrinsic geometry. This is what I was showing you before. The proof is unrolling a thread as I did before. Okay, we have the arc length parametrization. We said before, with respect to this arc length, I can take the derivative of the arc length called S with respect to the original parameter T. These are computations that you should already have seen for curves. Okay, so we are just skipping them. The important thing is the fact that if I take the velocity of the curve with respect to this particular parameterization, almost tautologically, I would say this length is 1. So when we have a curve, we can always reparameterize the curve in such a way that the tangent vector has length 1. Okay, why do we need curves and so on? Well, we need this for this observation. Now we want to describe the curvature of something. Okay, this was the beginning. The topic of this lecture is define, understand, and measure, compute the curvature. First of all, define what is the curvature. Well, we start with, we all have an intuitive idea of what curvature means. And I showed you this because I was asking in the beginning of the lecture, is this space curved? And you were giving me an answer. So this means that you have an idea of what is a curved space, what does curvature means, and so on. Now we want to specify this notion. Well, a way to measure the curvature is, the point is that we have several ways to measure the curvature. Okay, several really means really several ways. And this leads, according to the way you measure the curvature, to several different notions of curvature. I was talking about intrinsic notion and extrinsic notion. Okay, we have several extrinsic curvatures, we will see. And so we have extrinsic and intrinsic curvatures. So let's start with one of this, of this point of view. Okay, so in order to distinguish the curvature of the curve, we are starting with how much is a curve curved. Okay, then we will see a surface, then we will see a n-dimensional submanifold of Rn plus 1. Okay, so we can just take the tangent vector. This capital T is the tangent vector of the curve. So you have, we can do this. We have the curve, we take the tangent vector to the curve, and we take its derivative when going through the curve. Do you agree that if the derivative is very high, that means that this tangent vector is changing very quick? And this means that the shape is changing very very fast. Okay, so this derivative is giving you an idea of how much is curved this curve. Okay, once you make some computation, you discover that the derivative of the tangent vector, if you use the the length parametrization, and we will always use that one to start for a curve, the tangent vector is orthogonal to the curve. Also geometrically, it's very clear. And so you can say that the curvature of this curve, if you're looking for one number expressing the curvature, you can say the number is this k. How much longer is the derivative of the tangent vector with respect to the normal versor? This is a vector of length 1, this bold face n. Okay? And this is the only number for the curve in a plane, measuring how much this curve is curved. Okay, I let you notice that, by the way, we can use one number, but technically the derivative, the quantity measuring the curvature of this curve is a vector. Moreover, this is a vector in a certain point. If I want to measure the curvature in every point, this will become a vector for every point. In mathematical language, a section of the tangent bundle to R square, because this is a vector, the normal vector is not tangent to the curve. Is that clear? But it is a tangent vector. To what? To the ambient space. Just a matter of terminology. And I'm not saying anything fancy. I'm just saying, I would say, trivial things. The normal vector is a vector, I'm saying. Yes, it is a vector in R square. In that point, so it is a tangent vector in that point. But I'm considering the normal vector not on all the space R square. I'm considering the normal vector only on the image of the curve. So the curvature, in some sense, is something taking values in a bundle. No, this is a vector bundle. I use the word bundle in the first part of the lecture. Okay, this is the tangent vector tangent bundle to R square restricted to the curve. So it is a vector bundle on the curve. Okay, just let you notice that. And of course, we can talk about curvature with sign, because if you think about it, all that I'm saying depends on the orientation of the normal vector. If I take the normal vector in the other direction, inside or outside the curve, then I obtain different things. Okay, so you can see that everything here, it's depending on the embedding, and not only on the embedding, also on the orientation of the embedding. How is the curve? How do we say this is positively oriented or negatively oriented, and so on? Okay, and from this notion, there are the rules that you maybe know as the right-hand rule and the left-hand rule in the space, stating where a third vector is going if we want to preserve the orientation starting with two vectors which are oriented in a certain way. Okay. Anyway, if you do this kind of computation on the circle, you obtain what you would expect, that the curvature of a circle is just the inverse of the radius. Okay. And okay, before chapter D, just to put all of this in something that you probably already know. I'm sure you know, because I have seen these formulas on the blackboard in Roberto's office a few days ago. These are the Frene formula, and these are formulas for a curve in R3. So for the moment, we were talking about a curve in R square in the plane. If you take the curve in R3, well, when you obtain this derivative of the tangent vector and you discover that this is normal to the curve, if you try taking again the derivative of the normal vector, you discover that you end in a different direction. A direction which is a combination, of course, it is different, not dependent. So, which is which can be expressed in a tangential direction with respect to the tangent vector, and another direction that it's called the binormal direction. Okay, and if you take again the derivative of this binormal direction, the cycle is over. You end in the normal direction. So if you go on with derivatives, you obtain nothing new. Okay, so these formulas are telling you everything about how the curve is embedded. Okay, and these are called the Frene formula. They give you a frame made by 3 vectors in every point of the curve, a frame which is from some point of view, a natural frame for looking at things if you are living on the curve, as we were saying before. There is a natural direction, which is the tangent direction, the only thing that I'm assuming you can see if you live in this world. But if you open your eyes, you can see that the outer space is much wider, and there are 2 other directions, the first order and the second order. Okay, because you see these directions arise from a derivative. Okay. Okay, in general, you can do this for every curve in Rn. You just need a technical assumption, and then you have a moving frame, a Frene frame. But now, when you take the derivative of the binormal, you have several other directions to fill. Well, it happens that you can fill all these directions, but taking successive derivatives. Okay, and you obtain a formula, a Frene formula, a Frene formula similar to that one, but including several other vectors. After the binormal, there is a vector which is sometimes called the trinormal, of course. I never heard about the terminology quadrinormal, I don't know, but it would make sense. And of course, at the last step, you still obtain the normal, and then the cycle is over. Okay? Well, this just to give a more general point of view, but now we can switch to surfaces in space. Now we have intrinsic geometry. What do I mean by we have intrinsic geometry now? But, well, I mean that unlike the thread, unlike the mouse cable that I was using before, if you take a portion of a sphere and you try unrolling it, that means put it in the air and you try to check if it flattens out, it becomes a piece of paper, a flat piece of paper. Well, this doesn't happen. And not because of you. This doesn't happen because it cannot happen. Because the sphere is, as surface, is intrinsically curved. Okay, and we will now talk about this. This was a very astonishing fact when it was discovered, and it is called, it's the only theorem that Gauss called egregium, which means very beautiful theorem in Latin, as we know, because it's also an Italian word. And now this section is to talk about this kind of curvature, which is called, of course, Gaussian curvature or total curvature of a surface. But first, an introduction. Again, the question is, what is the curvature? For the moment, for the curve, we have the answer. For a curve, there are several curvatures, which is that K, well, I didn't tell you this, but we can call this curvature, right? This is called torsion, actually, but it is a curvature of second order and so on. But we have a curvature well-defined, which is this one, and none of this number is intrinsic. They are all extrinsic, depends on how the curve is put in the space, okay? Well, for a surface, that means dimension 2, we pose the same question. What is the curvature? Okay, let's start doing the same. We want a way to measure it. I propose you two different ways. The first thing that we will investigate is taking sections, in the geometric sense, slices of the surface with planes. Okay? Normal sections means that the plane contains the normal vector. So we have the surface, we have the normal vector, and here we take any plane which is containing this vector. Okay? So we have several intersections with the surface. Every one of these intersections is a curve. And then we can take the curvature of the curve. Okay, so what I'm saying is this one. Okay, this is the picture. Okay, what I'm saying is that I'm here in a point P. I want to measure how much this surface is curved. I can say how much this line is curved, and so I just build geometrically this line. I do this for every line, and then I say something, okay? So I will have a lot of numbers telling me the surface in this direction is curved 3. The surface in this direction is curved 4, and so on, okay? And now we will discuss this, but for the moment, just you should have in mind this geometrical construction. We are doing geometry, okay? So you should try to look things when you can. We are in R3 just because we want to visualize them. Is this clear?
Yes.
Okay. Okay. Just one thing. If I take the plane and if I consider that the vector generating this plane is a tangent vector and the normal vector, if instead of vectors I take versors, I mean I restrict my attention to vectors of length 1, then this means that I have a map from S1, that is vectors of length 1, okay, on the tangent space in the point P, to real numbers. Is this clear? To every tangent vector, to have a tangent versor, I associate the curvature of the section made in this way with the surface. Okay, this is a number, so this is the number. So what I obtain is a map from the circle, from S1 to R. This is called Gauss map. I'm interested in this. We can make geometry with this Gauss map, of course, but I'm interested in this just to tell you that being a map which is continuous from S1 to R, S1 is compact, so we have a maximum and a minimum. Okay, standard theorem of calculus 1, a continuous real map periodic, that means on S1, as maximum and a minimum. Okay? It's also clear that the collection of all these numbers gives a fairly good picture of how the surface curves at P. And of course, having the maximum and the minimum, these are the most important number, I would say. Well, let's call this maximum and this minimum K1 and K2. We can call them curvatures, right? Also, I mean, if you want to synthesize this number in just one single number, what can you do? Well, you can take the average Okay, it makes sense. It is making sense, I mean. And how do you call it? Mean curvature. Sounds good. It's the mean of these two curvatures. Well, of course, also their product is relevant. I mean, these are all numbers. Of course, you can also take k1 squared plus k2 to the power of 7, of course. Okay, but I mean, these two numbers are symmetric polynomial in these two variables. So these two numbers, the sum and the product, are special. Just to check if there is a mathematician or somebody knowing very well linear algebra between you, what are you thinking to when I'm saying that the sum and the product are special polynomial, and I use the word symmetric polynomial? Is it something switching on in your mind? You are thinking to something, you are associating, you are thinking about some notion in linear algebra.
Well, into a symmetric matrix, the sum is traced. The product is the determinant, so we have two values of.
Okay, so we have a mathematician here, I would say, because he's saying he would call this the trace of a matrix, and this is the determinant of the matrix. Very, very correct. And in which case you obtain from a matrix the trace in this way and the determinant in this way. I mean, what are these K1 and K2 for the matrix? They are the eigenvalues. Another mathematician. Very, very good. Well, you deserve a spoiler. In general, that means no more surfaces in R3, but hypersurfaces in Rn+1, we will have a matrix, actually an endomorphism of the tangent space, which is more intrinsic than the matrix. We will have eigenvalues of this endomorphism, no more 2, but n. And these eigenvalues are called generalized curvatures of the manifold. And the determinant of this operator of the associated matrix will be called the Gaussian curvature or the total curvature. And the trace will be called the mean curvature. Okay? So this is a general notion. But here in R3, you can really visualize this. But now you have also the big picture, which is the next section. Okay. Now, just a remark. Probably the remark may be the remark that started it all for Gauss, who knows? But the remark is the following, very, very easy. If you reverse the normal direction, because this is, remember, this is done with the normal choice, okay? This is a normal vector of the surface in R3, and we can reverse it. We can choose the opposite. Well, if you choose the opposite, what happens to each single curvature, to K1 and to K2? If you reverse this, they switch sign. Of course, we already said this for curves. And then what happens to the mean curvature? It switches sign. And to the product, nothing happens. So, I mean, maybe it's not important, but at least it rings a bell. What do I mean? That we have already proved that K1, K2, and the mean curvature cannot be intrinsic because they depend on the most trivial thing we can choose of this of this thing. They depend on the direction we choose. Okay.
But Maurizio,
why?
sorry.
Yes.
What happens if I have an R3 surface embedded in R4 with 3 values of curvatures?
It's you have the eigenvalues of a certain operator that we will define later, and I have 3 curvatures, and the same also. Your question is?
Yeah, in this case, when I have the product of three curvatures, the Gaussian curvatures is always the same.
Okay, good point. Good point. In fact, this also only in even dimension.
Okay.
Okay. If you want the complete spoiler, then
no.
You're right. I'm giving you the big picture, so it's better we choose from top down, a top down explanation. Then, when we will have several curvatures, we can take all the symmetric polynomial of these curvatures. That means the coefficient of the characteristic polynomial of the endomorphism, of which the product is just the first term, and the trace is the n-1 term. Is that clear? So these are the extremum of a range of curvatures. Okay, these symmetric polynomial are what are called generalized curvature. And now I realize that probably before I said you something different. These are the principal curvatures, not the generalized curvatures. These are the generalized curvatures together with all other coefficients of the polynomial, of the characteristic polynomial, and okay, this depends on how we write the characteristic polynomials. I would say the even degree terms are intrinsic invariants in the sense I have told you, and the odd degree terms are not intrinsic invariant, but they depend only on the direction of the normal vector. It means that if you take the absolute value of them, then they are intrinsic invariant.
I see, okay.
Okay, and to complete this answer, what I'm saying holds for every of them except the mean curvature. The mean curvature is never intrinsic. It's strange. Right, I agree. It is written in a page later. Thank you. Anyway, this is the big. As you can see, the big picture is a little bit more complicated, but the principle, the essence is this one. We have several principal curvatures which are just eigenvalues. Corresponding, we have several principal directions, and from these principal curvatures, you can form symmetric polynomials with them, and in this way you obtain more or less, with certain caveats, you obtain more or less intrinsic invariance, at least taking the absolute value and not considering the mean curvature. Okay? So let's check, for instance, if you are looking to a cylinder and we want to compute the principal curvatures, how do you do? Well, you take a section, you just imagine it, and you see that the section is I would say it's always a circle also in this direction, but it's a circle with the radius which is bigger and bigger and bigger, right? And so this means that the curvature is smaller, smaller, smaller. The biggest one is this one. So the biggest principal curvature is 1 over A, and the smallest one, if you take the last section on the direttrice, on this line in the cylinder, then you obtain the second curvature is 0. And this means that their product, the total curvature, the Gaussian curvature, is 0. And this means, we will see why, but this means eventually that the cylinder is locally just the plane. In fact, you can unroll a cylinder. Just cut it and take this way, and it becomes a sheet of paper. Okay? And this tells you again that they are not isometric invariants. Because, of course, for a sheet of paper, you have 0 for everything, also for the single principal curvatures. So if we are saying that the cylinder is locally isometric to the piece of paper, then an isometric invariant, something intrinsic, should be always 0, not depending on the fact that the cylinder is put in the space in this way. Okay, we already have seen everything here, and I just stress out the word astonishing fact. I mean, I repeat, we define the Gaussian curvature as K1 times K2. Okay, this is K. K1 and K2 are depending very much from how the surface is embedded in the space. So you would expect that also their product depends, but this doesn't happen. I mean, it's a very surprising fact, right? That you put the surface in the space, you compute this number, very natural. You compute also K1 plus K2, another natural number. This one appears to be intrinsic. And this one means that maybe the surface that is embedded, it is embedded in R3, maybe it lives by its own. I mean, it has a live being by himself, because there is something intrinsic that will never change. Also, if you take this object out of R3 and you put everywhere else, or you just look at this object by itself. Okay, and this is the beginning of the notion of abstract manifold. Okay, so you see the importance of this remark, of this discover. I don't know how would you call that. Okay. And I told you at the beginning that we were going to measure the curvature in several different ways. One that we are using now is this one, that is take sections of the surface. Okay, so you take a section, you measure the curvature of the curve, and you take another section, and so on. You obtain a lot of curvatures. You take the minimum and the maximum, and then you say things. Now we are taking another point of view. We want to measure, as we did for curves, the derivative of the normal vector. Okay, this is giving another information, maybe a different information, we don't know. So we just take a tangent direction, and with respect to this tangent direction, we take the derivative, how much is this normal vector changing. Okay, so in order to measure how much this normal vector is changing, we need a derivative. And this is why this section is how to take directional derivatives in Euclidean space. And of course, we have already seen it in the first part of the course. And just as a check as usual means that I'm going to ask you a question. So Roberto, be prepared. How many directional derivatives do we know from previous lectures? Actually, I'm cheating because the directional derivative I'm talking about was just in the last part of my last lecture that we have never done. But I remember that Alberto did in the beginning of his lecture. So what is this directional derivative that we know in the Euclidean space and that it is shown in the next page? Everybody can answer, not only Roberto. The answer is actually very easy because...
Sorry, can you repeat the question?
The question is if you have a notion of directional derivative on a manifold. If you know how to do the derivative in a certain direction, okay, we call it directional derivative, well, you can tell me if you know how to do this in Rn, I hope you know, and then if you know the extension of this notion to general manifolds. And this was the beginning of the lecture on Lie groups. And I am quoting the word Lie. Louder?
I'm thinking, but I think that we have to choose a direction. But we have to consider an incremental
A curve starting from a point.
Yes, from the point we consider a curve, then we evaluate the function, what it is from the point at distance epsilon from the beginning point, okay, and then evaluate over the distance.
Oh.
And take the limit. That is the definition of the derivative with the reference of the direction.
Where is the direction in this?
We have considered
the curve.
Yes, we are considering the normal to the plane.
No normal up to this moment. In the last lecture, there was no notion of normal. Well, Roberto, do you have an answer?
We can take the normal.
Wait a moment.
We can take the derivative of the normal. Just with the...
Oh, this is what we are going to do. But now I'm asking about a derivative on a manifold. So abstract manifold, there is no normal direction. Okay, we have only tangent vectors. So I'm asking for the directional derivative of tangent vectors in the direction of tangent vectors. Roberto?
Was there something related to the vector field, the derivative with respect to a vector field?
Yes. But my suggestion that I was quoting the word Lie doesn't ring a bell, right?
Lie derivative?
Yeah, the Lie derivative.
With respect to vector field.
Okay. Okay, guys, I know I skipped it, so I'm very sorry. But anyway, this was the beginning of the lecture from Alberto. But since I skipped, this is very important. So we are just doing a quick recap of this notion, which is very important. And this is the abstract notion of how to take derivatives of everything intrinsic in a manifold. Okay? Everything, I mean every tensor on the manifold. And the notion is very, very simple. Maybe what you were trying to recall in your mind. Start from a point and a direction, of course, because we want to take the derivative in a certain direction. So we want the derivative in the point P in the direction of a certain tangent vector. I stress out tangent, and I repeat that in an abstract manifold, we have just tangent vectors. There is not normal. Normal is a concept related to the embedding. Moreover, if you're thinking about the normal direction, just one normal direction, the manifold has dimension n, and it is embedded in dimension n+1. The codimension of the embedding is 1. Otherwise, you will have several normal directions. That means that you can't anymore choose, you can't anymore say, I take the normal direction. What is the normal direction? Which one between the three-dimensional space, normal space that you have in this point? Okay, you see how many things are involved when you try to generalize things and to abstract things. In this sense, thinking to the manifold in an abstract way is removing not essential parts of everything. Okay, we are not interested in how the manifold is embedded, and so we remove it from the ambient space. In this lecture, we are interested because, as it turned out, as simple as it is for curves, if we want to talk about how the space is curved, this is intimately related to how the space is embedded in another space. Okay, but we are now talking about previous lectures. So intrinsic manifold, only tangent vectors. We have a point, we have a tangent direction. Okay, and I want to do the derivative of another tangent vector. Okay, if I want to do the derivative of a function, I already know how to do. The directional derivative of a function is the partial derivative of that function. You say, well, what does it mean, the partial derivative? We are in an abstract manifold. Okay, an abstract manifold is locally just like Rn. So you can take the partial derivative of that function in that Rn, and this works. Okay, but if you do this for a tangent vector, then this doesn't work locally, meaning that in this case, this depends on the identification you take of the chart around P. It depends on the chart. Okay, so you need another way to define the derivative. So what you were saying, correct me if I'm wrong, I think you were saying that I take a curve, which is not any curve, is the integral curve of this tangent vector. Remember, from ordinary differential equation, if you have a tangent direction in Rn, but locally this is Rn, you can locally integrate this tangent direction, and you can create a curve, going in this direction as much as it can. For every situation, you have a maximal integration path, okay? And then you have this curve, and I want to take the limit of the difference between this vector and this vector, the limit for the point that tends to P. Okay, this is more or less what you were trying to say. But what I just said is not possible. What is the difference of this with this? They live in different spaces. They are not in the same vector space. You say, oh, what are you saying? This is R square. Your screen is R square. So this is a vector. I can take this here and take the difference. Well, take this here means that you are embedded in Rn, but we are not. This is an intrinsic manifold. So how can you take this vector to here? As you can see, this notion of how can you connect the tangent space from here to here is very, very important. In the previous lectures, we decided to take this tangent space to this tangent space with a map which is called the flow, which is simply the differential of this map. I mean, this is taking the point P in a point phi of P. So this is a map of the manifold to itself. So we can take the induced map on tangent spaces, assuming you remember that if I have a map from two manifolds, then there is an induced local map, the first order approximation from the tangent space to the tangent space. And this means that this is a way of comparing the two tangent space. So I'm just using this map to take this vector here. And then I can take the difference and take the derivative. Okay? What I'm doing is called the Lie derivative. The Lie derivative of the vector field x of the vector field y in the direction x. Okay? And I want to point out that if we, as we are doing now, want to measure how the normal vector is changing, it means we want to take the derivative of the normal vector, y equal to the normal vector, right? So this is no more possible. Why? Because the normal vector is not a tangent vector to the manifold. Okay? So this works only when both of them are tangent vectors. Okay? But the normal vector is a section of a tangent bundle restricted to M, but not the tangent bundle to M. Okay, so this means that you cannot use this derivative for measuring how much the normal vector is changing. Is this clear? So this is the Lie derivative, and I just want to convince you that we already know a way of taking derivatives of vectors with respect to vectors, but this notion works only for tangent vectors. Now we want the notion of taking the derivative of the normal vector, which is on the other side of the ocean with respect to tangent vectors, and so we cannot use this Lie derivative. Okay? In some sense, we need a way to connect what? Not the tangent space here to the tangent space here, but something that we can call the normal space here to the normal space here. Okay, this is another point of view. We have vectors here which are not tangent, and we want to take the difference because we want to compare them with vectors here which are not tangent. If we can take the normal vectors here to the normal vectors here, then they are in the same vector space, and then we can take the difference. Okay, so we need a new way of connecting vector spaces over different points. We need a connection on vector bundles on these manifolds. This will be the last point of view, okay? But just to tell you that all this very complicated notion that if you see look at them from the very abstract point of view can be very difficult to understand, and the concept, what is behind them is very difficult to grasp. They are actually very simple ideas. Because we need, now it's apparent that we need a way to take normal vectors to normal vectors, connecting these kind of spaces. And they are not tangent space, so we need a connection on spaces which are not tangent. And in general, we are interested in how to connect different points of a manifold. Okay, you were asking?
Yes, the normal space not be seen as the derivation of the tangent space.
The normal space, if it can be seen as
the derivative of the tangent space.
So you are referring to the fact that if you have a tangent vector of a constant length and you take the derivative, you end in the normal direction. Yeah. This is a formula that holds also in this case, but I don't know if you are proposing a notion of derivative of a vector space as equal to another vector space. I mean, only if the tangent vector has constant length, I would say length equal to 1, maybe. Okay, no, constant length is enough. Then the derivative is normal. Okay, so I would say no. Maybe the notion, the related notion is the Gauss map, in the one that was defined on S1, now is defined on Sn-1, and it's giving you the derivative with respect to a certain tangent direction as a number that is expressing the normal component of this derivative. So, by the way, we need a directional derivative. Okay. And now I was talking about abstract manifolds and so on, but now, I mean, we start with simple things. First of all, I need a directional derivative in Rn. Okay. We already have it, of course. For instance, for functions, you know how to do the directional derivative. Okay. You take the limit of the incremental ratio this way, and we know from the intrinsic point of view that this is more or less by definition the tangent vector applied to the function f. Remember this language, okay? When I say that a tangent vector express the direction with respect to which I can take derivatives, then I said in the first lecture, let's take a leap in the future, in the abstract manifold, that is, let's call tangent vectors the derivations of functions. And that was, if you remember, the starting point of abstract manifolds. A tangent vector is a derivation on functions, on germs of functions, okay? And so this is intrinsic. We can do this in Rn and also on any manifold. So no problem for this. But remember that we want to take the derivative of the normal direction. So we want to take the derivative of a vector field. Okay? So what is the derivative of a vector field in the direction, in a direction? Now, think about it. Now we are in Rn. What is the derivative in a certain direction of a vector field in Rn? That means an arrow in every point of Rn. Okay? You just take the vector field in the point you are computing the derivative. The vector field in the other point, you connect this tangent space in Rn straight to the tangent space in the original point. You can do this because you are in Rn and you know that all tangent spaces are the same. You can say that a vector, let me draw a picture. You are in Rn, okay? You have a tangent vector here, and you want to take the directional derivative in this direction. Okay, so this is a tangent vector in a point, and this is the tangent vector field that you want to take the derivative of. This means that this y is defined on every other point of Rn. Let's just draw some of them. Okay, let's say these are all values of y. Okay, is this clear? I should write this is y on the point P, this is y on the point Q, if this is Q, and so on. Okay, please interrupt me if this is not clear, because this is very simple. It should be completely clear. And if I want to take the derivative in the direction xp of y computed in the point P, okay, what can I do? Well, the standard idea is just to connect these two vectors. I mean, this vector, just take it and take it here. You see, I'm implicitly stating that this tangent space and this tangent space can be connected by a canonical map that I can see here. a map which is related to some notion of parallelism, because you would agree that this vector is parallel. I could say, okay, the map is just given by parallel translation. Okay, I'm translating this vector in a parallel way. So I'm making a parallel transport of the vector. Okay, and this is, in some sense, canonical in Rn. I can see there is a notion of parallel transport. And then if I have this notion and I call this y prime q, then I can take the difference, yp minus y prime q, and divide by the distance that there is between p and q, or something like this. And then I can take the limit for q going to p. Everything makes sense, and this gives you another vector, which is measuring how much this vector is changing instantly in this point. Is this clear? Okay. Well, in order to do this, if I want to do this in Rn, I'm just doing this. I'm just taking the derivatives of the coefficient of the vector field. Assuming that the vector field y was just with this coordinate, then I'm just taking the partial derivatives of these components. And you see, in taking these partial derivatives, I'm implicitly assuming that these partial derivations are all the same in Rn. I can identify them. Okay, remember, I say it again because I think it's important. I'm saying that if
Maurizio,
yes,
maybe you should leave this picture and draw another paper. Maybe just, I don't know if you want to do the same plot so that in the notes we'll find it again.
okay, but I'm not actually. I don't think I will save these notes actually.
Okay.
But
no, as you wish.
I mean, they had Scrabbles, and I don't think they are very useful without the recording. So
yeah, clear.
And you will have them, of course, on the recording. But anyway, what I was saying is that if I have r squared and I have a point here and a very far point here, and I tell you the partial derivative here in the direction of x, assuming this is x, and the partial derivative in the direction of x here, you can say in some sense that they are the same. Okay, but if I have a manifold and I take a point here and the point here quite far from each other so that there is no common chart between them, so here I have two different charts, and I tell you this is the index. This makes sense with respect to this chart, because this chart means that this part of the manifold is just like this. Okay, and so the index here makes sense, so the index here makes sense. But then I say the same here, take the index in this other point. This is a chart that is giving you an isomorphism here, but you have no way of connecting, of saying that this is the same with respect to this. There is no overlapping, there is no connection between them. Okay, they are, I mean, these are isomorphisms, but of course you can find a different isomorphism. You just reparameterize Rn, and then the index is something different. Okay, so you are saying that this is equal to every the index in Rn. That doesn't make sense. Okay, so you see, saying that this is the same as this in Rn is just because Rn is a manifold with just one chart. Everything is global. Okay, so this means that this of directional derivatives cannot be done on general abstract manifolds. Okay, it's a special thing of Rn. So just remember this. And of course, this kind of directional derivatives is very special because it's the directional derivative in Rn. Come on, with the standard metric, the very good old friend Euclidean metric. Okay, this derivative, spoiler, is called the Levi-Civita connection of Rn. Is the metric connection of Rn. I told you in the beginning, the connection is a notion that is giving you geometry from a different point of view with respect to the metric, but when you have a metric, you have a unique associated connection, which is the Levi-Civita connection. And this D, spoiler, is the Levi-Civita connection of Rn. Okay, well, what are we doing with this Levi-Civita connection, with this derivative in Rn? Remember what we were looking at that for? To take derivatives of the normal vector of the manifold. So let's do it. This one. Oh, before doing this, let's have a look at properties of this derivative. So first of all, check. This derivative is a map. Let me open a new one. I say that this derivative is taking a vector, taking another vector, and giving you a third vector. Okay, in a more on Rn, I said on Rn, and this is, and then other vector fields on Rn, this is, and the result is a vector field on Rn, that is this. Okay, this is clear. Now, remember that I told you that this vector field can be just a tangent vector in a point. Okay, the fact that this is a tangent vector in a point is the sentence in mathematical language that this map is tensorial in X. This is just a terminology for the moment. I will explain this later, but for the moment, just in order you to get used to this kind of language. When a mathematician looks at this, the first question he will ask is this tensorial in some of the two components? And the answer is yes, it is tensorial in the first component. He is just asking if this map is really depending on the vector field, or it's defined also when the vector field is just a tangent vector. Okay? Well, this is just a matter of notation, but I want you to notice that since we are now, I mean, you could do the same, a similar map, no more called D, because D is this one on Rn, okay? But if you put here a manifold M, well, you can have the same. You can have a map taking vector fields on the manifold, making the derivative on another vector field on the manifold, and giving you a vector field on the manifold. For instance, the Lie derivative is something like this. And now, what we are going to use is something more general, is something that here has vector field on M, and here has vector fields no more on M, no more on Rn, but no more vector fields, but sections of the tangent space to Rn. You could say, oh, vector fields on Rn. No, tangent vectors to Rn, but tangent to point of M. Because this is the normal. Okay, the normal versor or vector is such a vector field. And to take now the derivative in a tangent direction of the normal vector field. Okay, the derivative, let's say this. And we will obtain another vector field. But all these vector fields are vector fields on the manifold. So they are not vector fields on Rn. Okay, are vector fields of Rn, but restricted as vectors only to points in the manifold. Okay? Okay, this is just the reason of all these notation here. Okay, properties. First property, the derivative is f linear in x, which is what I was telling you. It is tensorial, it is defined pointwise. More on this later. For the moment, remember that a lot of theorems or propositions will state that a certain operator is f linear. F are the C infinity function. Okay, means that if you put a function in front of x, if you take the derivative of f times a tangent vector of y, this is just f times this. A very natural linearity, okay? But with respect to functions, not with respect to numbers. You know, this is not always true. For instance, this is a derivative. So what you expect if you take the derivative of f times y, do you really expect that you can take out linearly f? Come on, this is a derivative, means that there is some Leibniz rule, okay? So it will be something like derivative of f times y plus f times derivative of y in some sense. Okay, of course, here there is x, here there is x, and this is the formula, of course, with parentheses here. Okay, so this is not always true, the linearity for C infinity function. Oh yes, this is the formula I was referring to. Okay, let's finish this part and then we can take a pause. Now, two properties of the directional derivative, two objects associated to the directional derivative. If you look at this directional derivative in local coordinates, what happens? Look at this. If you take the directional derivatives in local coordinates, means take a certain tangent vector that you like. What is a tangent vector that you like? Instead of a general x tangent vector, choose one that you like in Rn. Choose one. Okay, you are thinking to tangent vector. Here there was the answer 1, 0, 0, 0, 0. This means that you are thinking to tangent vectors as vectors. Okay, first lecture I told you we can think to tangent vector in three ways. This is one, correct, but I want another one as a derivation.
Yeah,
so
the partial derivative.
Called also day in the x. Okay, this is what you mean by the first. This is what you mean by 1, 0, 0, 0, 0, 0, and so on. Okay, so let's take the derivative in the direction day in the x of what? Of another. day in the y, or day in the x1, day in the x2. Okay, but let's talk simple. Okay, so if you do this, you discover that this is not zero. Okay, but if you take the symmetric, you exchange them, you can take the derivative in the direction in the y of in the x, and you discover that they are equal. So in some sense, this difference, which is zero in this case, is measuring if this is symmetric or not. Well, it appears that actually this is not zero. I mean, this is zero, but this zero is actually given by the bracket. You remember the bracket between vector fields, between the in the x and the in the y. And so this is just to say that for the connection in Rn, there is this formula. This formula means that the connection is symmetric in some sense. Okay? And so it makes sense to say, okay, when we have a connection in general, let's consider this quantity, which in this case, I repeat, is zero. Okay? But in general, let's call this quantity the torsion of the connection. And so we should remember that when we have a connection made in this way, the torsion is measuring how far is this connection from being symmetric in some sense. Well, I don't want to spend a lot of time on this torsion because for general connections on vector bundles it is not defined, but I want to spend some time on this point of view. What is this point of view? Well, this is just a different point of view of this map. You see, look at this map just in an algorithmic, from an algorithmic point of view. You put in this map one vector and you obtain something, a black box, in which you can put inside one vector to obtain one vector. So this is a map that you put inside one vector and you obtain what? A black box that take vectors and give back vectors. So you obtain an endomorphism of vectors. So can you understand? This is just the same as this. It's just a different point of view. Okay, just I'm saying that a function from R squared to R is actually a function from R to the space of function on R. Because I put one number as x here, and I obtain the same function, but with the first component given, and this is a function of only one variable, so it is a function. Okay, I agree that usually this is much simpler than this. But assume that this function is actually a parametrization of functions on R. And so the first component, x, is actually a weight, is actually a parameter with a special role. In that case, this is the correct point of view. That it is also giving you a different role of the parameter. You can take the derivative with respect to the parameter, but this will be, in semantic sense, different from the derivative with respect to the other variables. Okay? So, I mean, nothing strange in considering this map in this way. And why we do this? For a very important reason. Well, and now we have vector fields here, and endomorphism here. You know that on vector fields we can take the bracket. I just told you. Well, this bracket is a product. It's called the Lie product in the Lie algebra of vector field, because vector fields have a particular structure that is the structure of a Lie algebra, and probably Alberto told about that, but I don't want to delve into that. Just there is this natural product, okay? And by the way, for endomorphism, we have another product, right? What is this other product? And okay, in the endomorphism, we have a natural product, which is this one. Okay, just not the normal product. And we are asking whether this map is preserving these two structures of Lie algebra. I mean, what I'm saying is that on the two spaces, we have a structure with the same name. They are both Lie algebras in a natural way. Okay, you can say this is not really very natural. Okay, but it is natural. And so, is this map preserving this natural structure of Lie algebras? That means, is taking the Lie product as an endomorphism the same as taking the Lie product as vector fields and then applying the map? Okay. What I'm asking is the same as taking R with the sum to R plus with the product. I take a map that take X to its exponential. Is this map preserving this group structure with this group structure? Is this map transforming one structure in the other? Yes. And you see, this is important. I mean, this is the famous formula equal to AI times AB. This formula is not important because of the formula, but it is so important because it expresses the fact that these two quite different sets, I mean, one is every number, including negative numbers. The other one is only positive, strictly positive numbers. These two sets are completely the same from the point of view of the multiplication here and addition here. That means whatever theorem you prove here regarding addition in R, you can translate in a new theorem, but actually exactly the same, about multiplication in R plus, and vice versa, with the opposite, with the inverse map, which is, by the way, the logarithm, which is transforming the product in sum. Okay, so when you have, what I want to say is that when you have structure on a space and a similar structure on a space, in that example, the similar structure is the structure of abelian group. In this case, it's the structure of Lie algebra, okay? It's a natural question to ask whether a map is preserving this structure. And this is preserving the structure, okay? And when you have such a property and you want to measure whether a map is how much a map is preserving or not the structure, it's very natural to take the difference. So you can take the difference of these two quantities, okay? And if this quantity is 0, then you say, okay, the structure is preserved. It is different from 0, then you say, okay, this quantity is measuring how much the structure is not preserved, okay? Well, this quantity should be a drum roll, is the quantity we were looking for. It is the curvature. This quantity, which is not a number, as I told you in the beginning, is a very complicated quantity, depending on x, on y, and now you have an endomorphism. So it depends again on another vector field z, and if you put this vector field in the endomorphism, you obtain finally another vector field. So this quantity, which is expressed by 4 dimensions, by 4 vector fields, this is the famous curvature we were looking for. This is the object that when it is 0, it is not a number. So being 0 means being 0 for every choice of x, y, z, and w. So being 0 is a very, very strong condition. When it is 0 and only when it is 0, then the space will be undistinguishable, not distinguishable from the flat dear old friend Rm, called also the Euclidean space. Okay? What I just said, it's a theorem. I'm not asking you to trust me and just spoiling everything. Yes?
Sorry, probably we explain later. But okay for the bracket that is what is the bracket this comma the epsilon. But what is the epsilon bracket?
This one.
How do you
this one.
Yes. How do you identify those terms?
Or the you mean how is this bracket defined?
Yes, I understand the first term of the
yes. So if I understand your question, is x, y are vector fields on a manifold. Okay. Then what is this? Is this?
Yes. How is defined capital D over that?
Well, this is first. This is a vector field. Trust me, and I can explain if you want. But once this is a vector field, call it z, and so the directional derivative with respect to this vector field is just the directional derivative with respect to z. So you are asking if this is true, if this is a vector field, and which vector field is. Okay, so do you agree that x is a tangent vector, means that it acts on functions? Tangent vectors are derivations. Okay. So do you agree that this is a function? So this means you can take the derivative in the y direction. And you can take also the derivative in the x direction of y of f.
Yes.
Okay. So you can take also the, okay, that's already here. You can take xy of f minus yx of f. Perfect. Well, if you do this, this is tensorial. That means that if you multiply times a function, then this multiplication, you can take it out everything. This is strange because these are derivations. Well, it's not so strange because there is this minus sign and something is taking out and everything works. So this means that in other language, this is a vector field on M. The vector field on M is a derivation of functions, okay? So this means that if you have a function, you can take this on the function, defined this way. And the fact, when I say it's a vector field, I mean it is linear with respect to function here, and it is a derivation. Okay, so you can you can try this property, and it works. Okay, this is the other part of the course. This is an operation that is on tangent vector fields. And so you can take the derivative, and so you have the curvature. Okay, so the curvature is just this object. Okay. So for the moment we have the torsion, and for the directional derivative, the torsion is 0. The curvature, and for the directional derivative in Rn, this curvature is 0. And now we have another remark. If you take the derivative of the scalar product, this is the same. You see, this is a Leibniz rule. Just look at the scalar product as the product. Well, the directional derivative in Rn is so nice that it is also satisfying this rule, this Leibniz rule with respect to the product. We say that it is compatible with the metric. Okay, of course, all of this is true because the directional derivative, the Levi-Civita connection in Rn is very, very special, because Rn is the flat space. It's the space as good as you can think from the point of view of metric properties. Okay, and let me check. Okay, this is what I was saying. Okay, so 0 torsion, 0 curvature, and compatibility with the metric. Let me check if we can do. Okay, give me 5 minutes more, guys. I want to finish this this section, and then we can pause. So remember that I want to take the derivative. Up to this moment, we have the directional derivative of x of y in the direction of x for x and y tangent vector to Rn. But now I want to take the directional derivative when x is a tangent vector not to Rn but to M, a submanifold in Rn. And y will be in particular the normal vector, so will be in particular not tangent to M. So y will be a section of the tangent vector to Rn restricted to M. Okay, so I need to talk about vector fields on M, that means tangent, and vector fields along M, that means vectors which are not tangent. I mean, also tangent vectors works, are along M, but I can take a vector field also which is not tangent. Okay, when I say along M, I mean can be not tangent. I mean this. Okay, just a matter of terminology. And I still can take the directional derivatives. Do you remember I was defining the directional derivatives? Well, now here I'm defining the directional derivative in a tangent direction of any vector field, not only a tangent vector field to M. I just take the directional derivative of the coefficients. Everything works in this way because Rn, the tangent space in different points in Rn can be identified. Okay, so this di in the point P is the same derivative in another point. They can be canonically identified in Rn. Okay, and so this is what I was telling you. I have a directional derivative. This is the directional derivative I need. You can see that the arguments are, this is asymmetric, right? Not symmetric. You cannot switch these two parts. In particular, you cannot do anymore the torsion, because if you remember, the torsion was the derivative of x in the direction of y minus the derivative of y in the direction of x. Now you cannot anymore switch the two roles. The direction of derivation is special, okay? Is the direction of derivation. All the rest is something different. Okay, here we are, coffee time. Let me check first this. Okay, we told everything. Okay, very good, guys. I think we can stop here if you have questions.
Just a very short, Maurizio.
Yes.
Proposition 4.3, the last statement. Maybe it's the x of the inner product, or just x because it's meant as already as a derivative.
You mean this?
Yes. So it's the x of the inner product, or it's just x of the function.
So you say it's the x of this, or x or this?
Yeah, it's the same, no?
Yes, the answer is both, because they are the same. Because this is a function.
Yes, and yeah.
And the derivative, I mean, whatever definition we have done, we have given of directional derivatives in the direction of x, this definition on functions should be the classical directional derivatives. If not, the definition is, I mean, there is something wrong with it, okay?
Clear. Yeah, that's
in fact, this also. And for this, the same reason, this is equal to the Lie derivative of x of a function. I mean, also the Lie derivative is the directional derivative of functions. Okay, just because, I mean, in order to call it a derivative on functions should be the derivative.
Yeah,
okay?
Of scalar functions, yes.
Of scalar functions, yes.
Thank you.
You're welcome. Other questions?
How many minutes break do we have?
Okay, okay. So let's say, I mean, we have so many interesting things to say, but I can give you 11. So we will meet again at 5 to 5. 5 to 5.
Okay, thank you.
Okay.
We run.
Okay, let's just start with this recap. So on this space, on this space, we have the directional derivative. The directional derivative is very simple. We just take the derivative of the coefficients of the vector fields. This is the classical Einstein notation, where we are summing along indexes that are one on the top, one on the bottom. And the directional derivative of this vector field is just the vector field given by the directional derivative of the coefficients. This is giving in a more intrinsic way an operator that can be fed with two vectors and giving another vectors. And this operations is what is called connection. In Rn, this connection is usually denoted by capital D, at least in this book, and this nabla notation is more standard for the general Levi-Civita connection, or for a general connection on an abstract manifold. But what is important are the properties of this connection, of this operation on vector fields, that is infinitely linear with respect to one argument, that is tensorial with respect to the first argument, the direction of derivation, and it is a derivation, satisfies this Leibniz-like rule on the second argument, okay? And these two properties are the ones giving the abstract notion of connection for later. Then other quantities associated to this connection are the torsion, which makes sense only when x and y have similar roles, because you need to swap them, you see. And then I would say more important notion, the notion of curvature, which is this tensor. By this tensor, I mean the operations that you obtain on vector fields given by this expression. Remember that in this expression, there is still space left for vector fields. I mean, this is the derivation with respect to a certain vector field, so it must be filled with another vector, and the result is another vector. So this means that this is not a number and not a vector. This is a map between vectors. Okay? So this means that we already put two vector fields inside, but we still have space left for two other vector fields. Okay? Or we still have space for one vector field, and we obtain a vector field. So technically, we have space for one vector field and for one form. Because remember that vector fields are the dual of the dual, so they are linear maps on forms, if you remember this point of view. Anyway, this is what we mean when we say that this vector field, that this tensor is of type 3-1, 3 vectors and 1 form. Or when we say that this tensor has 4 indexes, 3 are below and 1 is above, or the opposite. I never remember which of the two. I think what I said. Okay, then another remark for the connection in Rn is that it is compatible with the scalar product, where compatible means this. That is a Leibniz-like rule. You see here I wrote the nabla x, but as Roberto remarked, this is the same as just x or yz. Okay, here I write this to make explicit that this is a Leibniz rule. Okay, and then we remark that all of this makes sense also when the second argument is no more a vector field tangent to the manifold, but something more. It's still a vector field along the manifold, but the vector can be also in another direction, not only the tangent direction to M, but also other directions. In particular, we will be interested in the normal direction. Okay. And this is the second point of view I was talking about in the beginning of this lecture. That is, instead of taking the normal sections of a surface, remember, I was taking sections, and so I obtained curves, and I measured the curvature of these curves, and I said, okay, let's take the minimum one, the maximum one, let's call them principal curvatures, then I have the product, then I have the mean curvature, and so on. Now I want to take another point of view, which is more similar to the point of view that I took for curves. I want to take one vector along the surface that will be the normal versor, but I could take any other vector maybe, and just measure how much this vector is changing along a certain direction. So I want to take the derivative of this normal direction with respect to a tangent direction. And for this, we need this derivative. This is why we were talking about this. Okay? The derivative of any vector along the manifold in the direction x. Okay. So this is the picture. So we have a point here. In this point, we have a normal vector, versor, length 1. And as I told you before, this normal direction exists also around P. Okay? Be careful, this exists one normal direction because we have a surface in R3. Or more in general, when we have a hypersurface in Rn plus 1. This will be the topic of the section 9, okay? But starting from now, just think about it. This chapter is just for surfaces in R3. But I mean, it's useful if you can always think also to the general case. Okay, so chapter 9 will be almost already done when we arrive there. And okay, so we want to change how much the normal versor is changing the direction of xp. Okay, so we take the derivative. Can you see that everything is going smoothly? There is a main line, a main topic in the way I'm telling you all the story. Okay, so we are now measuring the curvature just by measuring how much the normal direction is changing in a fixed direction. Tangent direction, normal direction. And well, we call this new vector that we obtain, do you agree this is a new vector field, okay? A new vector in P, actually, not a vector field, just a vector in P. Just a question, is this vector that I obtain tangent in P or not?
Yes, it is.
Yes, it is, but I mean, you are guessing, you have an argument, you think it is, or? You can say that.
Take the scalar product with n. If you take the scalar product with n, you get 0 because the normal is a unit norm.
Okay, so you are saying maybe something like this?
Ah, yes, sure.
Okay, so well, the answer here is yes, I think yes, but I don't have a proof yet. And what you have said is actually the proof, which is this one. I would say that there is also another argument that I like. Just take the normal section given by this tangent vector and this normal direction. Then you have a curve, and this is the normal direction in the curve. You have a planar curve, and you already know that taking the derivative in this direction of the normal vector is tangent. Okay, but anyway, yes, the reason is just this one. And this is an important fact, because this means that if you call, okay, we just call this image, this vector, we denote it by the capital L, and we call it the shape operator. We are just saying that the shape operator is an endomorphism of the tangent space in the point. Okay? And you know everything else because we already said this endomorphism, choose an orthonormal basis, show that with respect to the orthonormal basis of the tangent space, the matrix is symmetric. And when you have a symmetric matrix, what can you say about the eigenvalues? They are all real. Spectral theorem, maybe you call it this way. Well, so the eigenvalues of this endomorphism are all real. Of course, they doesn't depend on the choice of the basis. They are a characteristic of the endomorphism, and these are called the principal curvature of your manifold. And now everything we already said starts. Take the characteristic polynomial. The coefficients of the characteristic polynomial are just symmetric combinations of a certain degree of the principal curvatures, and these are the generalized curvature of the manifold. One of them is the total one of them is the mean curvature, and in the middle you have other general curvature. You see that the big picture is already done, actually. And what we are doing here in this section is just repeating it and studying it in the case of surfaces in R3. So, This is the shape operator. Another name that maybe you use in some situation is the Weingarten map of the surface, okay? And of course, this is depending on the embedding, and spoiler, this is known also as the second fundamental form of the surface. I guess you know also this name. Spoiler, the first fundamental form is just the scalar product, okay? So the first fundamental form is intrinsic. I mean, there is nothing more intrinsic than the metric, which is defined on the manifold. And the second fundamental form is not, because it's the shape operator, which is depending on the embedding. Okay, we will be more precise on this, but just to tell you that we are not saying anything that you don't know already, because I'm assuming, of course, when I say you already know this, I'm assuming you have already done some course in geometry of curves and surfaces. So you can compute the curvature, the torsion of a curve. You can already compute the Gaussian curvature of a surface in the space. If this is not the case, so don't worry, you're just learning right now. You know now that if you attend a course in geometry of curves and surfaces, they will talk about first and second fundamental form. They will use symbols, capital E, F, G, small e, F, G, which are the coefficients of these fundamental forms, and I will tell you what these are. But they are just talking about this notion. Fundamental form equals metric and shape operator. Now, this is an important formula. Just remember then, when you take the scalar product of the image under L of a vector, and you take the scalar product with respect to another tangent vector, this is a number, okay? This number is exactly how much is the component of the directional derivative in the normal direction. So this is really very important. You should remember this. If x and y are tangent to M, okay, not to R3. So they are not every vector in R3, just two tangent vectors. And you take the derivative of one with respect to the other, you obtain a vector which is not tangent to the original manifold. Is that clear? Because this derivative, capital D, is the derivative in R3. There is no reason why you should obtain something which is already in the manifold. Okay, you exit the tangent space of the manifold because this derivative is agnostic of the embedding of the manifold. Okay, the derivative is in R3. She doesn't know anything about the manifold. And so cannot infer from the fact that these are tangent that the output should be tangent. So in particular, this derivative will have a tangential component and the normal component. The shape operator is giving you the normal component in this way. And the tangential component is the Levi-Civita connection of the manifold. That is the intrinsic connection that I told you it is uniquely associated to the metric on the manifold. And why they are connected in this beautiful way? Well, because the metric on the manifold is not just a metric, it's the metric induced by the Euclidean metric in R3. So it makes sense that they are connected. Of course, if you put on M another metric, this doesn't work, but if you put on M another metric, you would never say let M be a surface in R3 in a book on geometry, because here, as I told you at the beginning of the lecture, I'm implicitly saying let M be a Riemannian manifold in the Euclidean space R3, and let be the Riemannian metric on M exactly the metric induced by the Euclidean metric in R3. You see that if I have to say this explicitly in every theorem, in every statement, the book would be 2,000 pages instead of, I don't know, 400. Okay, so anyway, remember that the exterior derivative, the directional derivative in R3 of two tangent vectors to a surface can go outside, and we usually go outside of the manifold. And if you want the connection on the manifold, you just take the tangent component. And the other part, the normal component, is giving you the other part, that is the second fundamental form, that is the Weingarten operator. Okay? Now, I told you that if you take an orthonormal basis, then the matrix associated to the shape operator is symmetric, okay? In intrinsic term, this means just that the shape operator is the technical word corresponding to symmetric matrix is self-adjoint. Means that if I do this, you see I can swap, I can use the scalar product to swap L from one side to the other. Okay, so the eigenvalues are real. Very good. And if we have real eigenvalues, then we have principal directions, eigenvectors, and we have curvatures, the eigenvalues. Okay, I'm going through this part because, as you can see, nothing is highlighted because we already said everything. Of course, everything we are saying, there is a proof, okay, in the language that we are skipping. We are not having proofs in this course because it is a crash course, but if you have questions about them, of course, ask and stop me. So, proposition, the principal directions, remember that the principal directions is something we already defined in terms of normal sections. The principal directions are the directions, the normal direction, the direction that when taking the normal section gives you the minimum and the maximum of the Gauss map. As before, okay? So apparently completely different from what we are talking about now. Well, theorem, proposition, that principal directions are actually the eigenvectors of the shape operator. This is what I was telling you. The 2 points of view are just different points of view of the same thing. But actually, if you think about it, the shape operator is the one giving you the generalization to no more a surface in R3, but a hypersurface in Rn+1. Because in that case, you can say I have a maximum and the minimum value when I take sections. Yes, you can still take sections, okay? Well, yes, you can still take sections. We have curves. You have a map from the n-dimensional sphere, n-1-dimensional sphere. You have a Gauss map again, which is compact, the domain of this Gauss map. So, as usual, Weierstrass theorem, you can say there is a minimum and the maximum. That will be the minimum and the maximum of the eigenvalues. But how do you obtain from this point of view the other eigenvalues? Okay, so this is the point of view that you can use to generalize these notions to higher dimension. Okay, here is the proof. As you can see, it's not the short proof, proving that this point of view is the same as the previous point of view. You have to make computations. And now, now that you have this link between the two notions, you can say, what is the Gaussian curvature? Well, the Gaussian curvature is the determinant, because the product of the eigenvalues is just the determinant. And you can also compute this Gaussian curvature in terms of the shape operator, because the eigenvalues, you can compute them in this way. Okay, and if you take an orthonormal basis, then you make a computation starting from coordinates here, and you discover that the Gaussian curvature is just this one. This is giving, when instead of E1, E2, and so on, you put the standard vector field, day in the X, day in the Y, day in the Z, and you make computation, then you obtain formulas that maybe you already know about the Gaussian curvatures in local coordinates, okay? Usually, these vectors, actually, when you have a surface in the original language from the Geometry 1 course, you probably, the surface is parameterized by parameters that you probably call U and V, right? These are points in R square, means that your surface is just a map from R square into R3. This is the parametrization, okay? And then in R3, you add the derivative with respect to U and the derivative with respect to V. And these are E1 and E2. And these are the terms giving you the coefficients of the fundamental forms and so on. Okay, just to. Okay, I was just spoiling this, this page, this slide. So if that wasn't clear, when we say first and second fundamental form, we mean bilinear forms. Okay, not differential forms. This is a form in a different sense from the previous part of these lectures. In particular, we mean symmetric bilinear forms, okay, that can be associated to matrices, of course. And the first fundamental form, as I told you, is just the metric on the tangent space. And the second fundamental form is just the shape operator. Of course, since I want a bilinear map instead of an endomorphism, I need to lower Riemann index. I mean, when I obtain the image vector, I just, how do you say, saturate the index, eliminate that with the scalar product, and then you obtain a map into R. But you need to fit this map with two vectors, okay? And so you obtain a bilinear map on the tangent space, which is perfectly equivalent to the original map. Is that clear? Because this scalar product has a property that this map is completely identified by the values that the scalar product has on every vector here in the second component. This is the property which is called the scalar product is non-degenerate, okay? Meaning that you cannot have, I mean, if you have something here and the scalar product with every vector is a certain one, then these scalar products completely identify the first lot. Okay, this is something called the scalar product is non-degenerate. This means that when you do something like this, you're not losing or adding information of any kind. It's just a different point of view. Okay. Okay. These two fundamental forms encode much of the geometry of the surface contained in R3. Why I added contained in R3? Because the geometry of the surface M can let you think about just the intrinsic geometry. When I say the geometry of the surface M contained in R3, I'm saying that I'm also interested in the way this surface is contained in R3. Okay, you see, I mean, I'm trying to teach you also some nuances that we mathematicians use when communicating. I'm telling you that putting contain in R3 and not putting it has two different meanings. And I'm also saying that this is, of course, not univocally defined, as you can see from the fact that this beautiful book here doesn't put it, and I decided that maybe it's better to put it, okay? Because the two fundamental forms encode much of the geometry for what we have said, both intrinsic and extrinsic, because the first one is intrinsic, the second one is extrinsic. Okay, so we need to be more precise and state that we are looking at the global picture of the embedding. And if you take any basis for the tangent space, then you have the famous coefficients that you can recognize. And the metric is just this. And with the small symbols, you denote the coefficients of the second fundamental form. And here, this is what I was telling you, okay? That usually when you have the embedding with two parameters, u and v, so you have three components in R3 of your surface, you can take the partial derivative of this vector with respect to u and with respect to v. And these are particular tangent vectors, okay? Which are the tangent vectors of the embedding. This is R3, this is R2, your surface. And I'm just saying that in this point, I'm taking the derivative with respect to u that will give a tangent vector to this coordinate line, and the derivative with respect to v, which will give a tangent vector with respect to this line. So I'm saying that this map gives you special tangent vectors. Of course, you can take also this and this. Okay, but the first two are more natural. But why? Remember why they are natural. Because these lines correspond to special lines in R square. But remember that R square can be reparametrized in almost every way you like, if you don't ask for any special property of the reparametrization. That means that the special directions actually are specific of this embedding of this map. Because if you reparametrize R square, everything changes, okay? So in this sense, we are doing some extrinsic geometry. Anyway, just as a global remark, very much related to this topic, I want you to think about the fact that often we do something in geometry, in calculus, which we consider natural, and it is natural in some sense because we use as vectors, as a prototype of a vector space, Rn. And Rn has special directions, which are, because Rn is defined as the tuples. The pairs R2 are pairs x and y. So I have the direction 1, 0 and the direction 0, 1. Okay, in some sense, in fact, this is called the canonical basis of Rn. Rn is special with respect to any other abstract vector space, because a vector space of dimension n, from one point of view, is nothing different from Rn. But from another point of view, is very, very different. It's much poorer than Rn, because doesn't exist a canonical basis. And in fact, you can say this is isomorphic to Rn only when you choose a basis. Okay, so in some sense, I'm saying that Rn is special, is a privileged vector space. And this means that sometimes we don't realize, but we do things that are related to this particular choice of a basis in Rn. And sometimes this is not really what we want. Now, in this moment, I'm thinking to the gradient descent algorithm, where the gradient is strictly linked to this choice. But this is completely another topic for another kind of lectures. Okay, just as a divertissement, I will show you, I will tell you that two apparently very different surfaces, which are the catenoid and the helicoid, now I'm describing you, are locally isometric. And remember, locally isometric means that if you cut them in some way, then you can develop one of them into the other. Okay, just like the thread, S1 is locally isometric to an open interval. It means that if you cut S1, then S1 is just an interval. This is locally isometric to a cylinder. Okay, a piece of paper is locally isometric to a cylinder because if I cut it, it becomes just a piece of paper. And the torus is not locally isometric to this because try cutting it, but you are not obtaining this piece of paper. Okay, the catenoid is this curve. Okay, this curve is this equation, but doesn't mind. Just take this curve in this way, rotate around the z-axis, and you obtain a very nice picture, which is this one. Okay, now imagine cutting up a meridian, one of these lines. Choose one of them, cut it, and hang up the catenoid. Use the gravity to reshape the catenoid. Which kind of object do you think you will end up? Let me check if you are really engineer. I would never be able to answer this question, of course. I know the answer because I read it and I was surprised and I said, I will ask this. Is the question clear? You cut here, you put this horizontal, this line, and you let the gravity take the other part down. And I'm asking you which kind of shape you obtain. Et voila! You obtain an helicoid. I think this is impressive. The helicoid is just made by a pen rotating on the middle point and raising up in the meanwhile. Okay? And if you do this, this is an experiment, or if you like, a proof. I would call it a mathematical proof, maybe more a physical proof, that the catenoid is locally isometric to helicoid. Why this kind of deformations are locally isometries? Because I'm assuming that there is no elasticity in this material, okay? So it is not stretching. So distances are not changing. The same I was telling with the thread before. I mean, if the thread is elastic and can bend, can be stretched, okay, it doesn't work anymore. Distances are changing. Okay, so I'm assuming everything is rigid from a certain point of view, not rigid in the classical point, but the material cannot be stretched or something like this. And so locally, the distances are preserved. Okay. Okay, as usual, I have highlighted the exercise that I think would be useful for you to do. Of course, every exercise is nice, but some of them are more equal to the others. And we are at chapter 6. And finally, we will talk about the new notion, the new geometric notion I was talking from since the beginning, that is the notion of a connection. I told you in the beginning that geometry can be done in one way using a metric. Okay, that's fine, and that's very natural. That means a way of measuring distances, lengths, angles, and so on the tangent space. Very, very natural. But when we started looking at the notion of curvature, which is also very natural, we started taking derivatives. And we started asking ourselves, okay, I want to compare the normal vector in a point to the normal vector in another point. And then we said, oh my God, I need a way to connect these two tangent spaces, which are different. How can I do? Oh, okay, very, very good, no problem. We are in Rn, so I can just do parallel translation, taking one vector to the other. Okay, so no problem. But now we say, okay, but I would like also something more intrinsic. If I have just a manifold, not embedded in Rn, what can I do? Is there any standard canonical way of taking one vector in a tangent space and transport this vector to another tangent space? Okay, so can I connect two different tangent spaces? The answer is no. There is not a standard for a manifold, for a general manifold. But what we can do, since we are mathematicians, in this moment we are all mathematicians, of course, and so what we can do is to take the properties that we have seen, the directional derivative, let's say the parallel transport in Rn satisfies, and ask in some axiomatic sense for a similar object on a general manifold. Okay, so this is the meaning of this sentence. We extract from the directional derivative certain key properties that we already have seen, and we just call any map satisfying these properties a connection. Okay, and we remember that a connection is, since we are extracting properties of the derivative, okay, because we are taking properties of the directional derivative in Rn, we think to this connection as a way of taking directional derivatives in a general manifold. Okay, so which are these properties? This, you see, important means important, because this is the way a mathematician thinks about things. Meaning, we extracted information from a very specific case, that is Rn. And now we want to do something similar on a general manifold. So we say, okay, let's try. Assume we have some map this way that is a directional derivative. That means that I can take one vector field, which is the direction I used to take the derivative on. I can take another vector field, the vector field that I'm derivating, okay, and taking the derivative of this, and the result must be a third vector field. Okay, I'm not inventing anything. I'm just mimicking what I have already done in Rn. Okay, so remember, and remember, in particular, in this case, I cannot do the derivative on normal vector fields. Why? Because I have only the manifold. I have no more the manifold embedded in Rn. Okay, is that clear? Okay, so I have an abstract manifold. I'm assuming I have such a map. In order for such a map to have any hope to be a derivative, well, something should happen. First of all, I would say this must be tensorial in the first variable. Okay, that was a property we already remarked on the directional derivative in Rn. Or now this is a technical property. I don't want to focus very much on this, but it's very natural. Maybe you're thinking, oh, okay, I would never think about imposing this condition, but it is really very natural. But don't think about this. But I want you to agree that this property, it is very natural. Okay? Because this is a derivative, so the derivative of a product must be the product, the Leibniz rule on the product. And you say, oh, this is not the Leibniz rule. This is not the derivative in the direction of x of f. This is just x applied to f. Well, remember that if there is some justice in this world, if there is some power above us, then whatever we call derivative on functions must be the classical directional derivative on this function. That is, in local coordinates, this must be the partial derivative. Okay, not the partial, but the directional derivative in that direction. Okay, otherwise we have no rights to call anything derivative. It is not this way. So here I'm implicitly saying that this derivative can be applied also to functions, which is not apparent from here, and on function is just the standard derivative. Okay, so what I want to say, just nothing of this is a proof or a theorem. Okay, what I want to say is just convince you that everything we are doing is very natural, and so you don't have to be scared of in first place. Okay, first example of an affine connection on a manifold. Well, take Rn and take the directional derivative. This is an example of something satisfying these axioms. Do you agree? Well, these actions were taken from that. So it's the other way around, actually. Okay? So, of course, this is an example. And let's check what we can do. So we repeat every notion we have already looked at for the directional derivative. We try to repeat it in this abstract case. Well, I can take the torsion. The torsion, what is it, the torsion? Well, for the directional derivatives, I have seen that there is some vector field which was 0 for the directional derivatives in Rn, but here, I mean, do you have any reason to think this is 0 in general? Okay, if this would be 0 in the general case, this would mean that from these actions you can prove a theorem that that quantity is always 0. Okay, this is not the case. In general, this is not 0. That was a special property of Rn. And more important, you can define the curvature. And this is in general not 0. Okay, and special theorem for a general manifold, this is 0, and being this 0 means being 0 for several arguments. Okay, this is a type 4 tensor. Being 0 means that it is 0 whatever you put in each of the 4 slots. Okay, so being 0, it's a very strong condition. Well, theorem, this is 0 if and only if the manifold is locally isometric to Rn. This is the theorem I was referring before. This is, if you want, the end of the lecture. This is the invariant you were looking for. This is the quantity that is measuring in the most precise possible way, is measuring how far is your manifold from being locally isometric to Rn. Remember, every manifold is locally diffeomorphic to Rn. This is more or less the definition of the manifold. So now we are asking, is every manifold locally isometric to Rn? Not at all, as the donuts show you, as the sphere showed you. Okay, and then natural question, which one are the ones which are locally isometric to Rn? The ones satisfying this very, very strong condition. These are called flat manifolds. Okay. Okay. As you can see, I told you, whenever you define something on vector fields, then you ask, look, is there any chance that this map that I just defined on tensor fields is linear for functions? I mean, if I multiply x by a function, can I take the function out? Just as I would do in a linear map? If I multiply y by a function, can I take the function out? This question is, the shape of this question is this map F linear? F is the ring of C infinity function. Okay, F is just the C infinity of M. Okay, is another language. And you see that both the torsion and the curvature are F linear, the torsion in all its arguments and the curvature in the first 3 arguments. Okay, this means in general language, you should memorize that to be F linear is equivalent to the fact that you can put here a point. You can talk about the curvature in a vector field in a point, a vector in a point, a vector in a point. Okay, not for the 4th component. The 4th component must be a vector field. That means that must be defined in a small neighborhood of the point. Okay. If you think, if I tell you take the derivative in a direction of a vector field, it is clear that this can be just a tangent vector, right? I'm taking the derivative in this direction in this point. I don't need any other vector close by. But do you think it would make sense asking for the derivative of this vector? I mean, yes, maybe it makes sense, and the answer is 0 because it's constant. Okay, but the point is that this cannot be just a vector. This must be a vector field around P. If this is the point P, X can be XP, but Y must be Y, that is several vectors here. If you want to talk about the derivative of this vector field. So what I'm saying in another language, I would say that dxy is tensorial in X, but not in Y. I would say that dxy is F linear in X, but not in Y. Okay? Well, so when we have a connection, we can take derivatives. So, and we have this notion of curvature. Okay? So the statement I told you before about the curvature was not true for a general connection, of course. It's true only for this connection. So I will repeat it now. So I was saying, if we have a connection, we can take derivatives, so we can measure something. But since we want to measure something related to the metric, it would be very nice if, given a metric, there is a certain connection in some sense compatible with the metric. Well, it turns out that there is such a connection. When you have a metric, if similarly to what happens in Rn, we require for a connection which is compatible with the metric, that is, if I take the directional derivatives of the scalar product and we impose this condition that this is just the directional, the scalar product of these two. Okay, if we ask for the connection to be compatible with the scalar product, and since the directional derivative in Rn is, we ask also for the torsion of this connection to be zero, which are the two properties satisfied by the standard connection in Rn, well, it appears that there is only one connection satisfying these two properties on a Riemannian manifold. And so, game over, I would say, and we win, because we have the metric, we have also the notion of connection. They give, both of them, they give geometries. I'm disturbed by this. I mean, the metric is natural, but also the notion of derivation is natural and needed to obtain the notion of curvature and so on. Well, now everything is linked together. I can find a unique connection which is compatible with the metric. Okay? And in the proof that there is this metric, this connection compatible with the metric, it's very nice because the proof shows that if such a connection exists, that connection must satisfy this formula, where you see here there is the connection and here there isn't the connection. If the connection exists, it must satisfy this formula. What does it mean? Now, how can you show that this connection exists? You use this formula to define it. You say, okay, this formula defines my connection, and I will show that this object, if I call the connection, the derivative in the direction of x or y, the component along z, then this satisfies the actions of a connection. And it is compatible with the metric, and its torsion is zero. So this formula becomes the definition of the connection and becomes also a widely used formula when you do computation with the Levi-Civita connection. Whatever computation you are doing with the Levi-Civita connection, I'm suggesting you always take in mind that there is this formula giving the connection just as a function of derivatives and scalar product and Lie bracket, which are the operation, the natural operations you have on your tangent space. You see, this is something just like the Euler formula relating the Nepero number pi I, which is a 1 and 0, which is a beautiful formula combining very different objects in the same field, which is really a field which is R complex numbers and so on. Here you have the tangent space with several notions, derivatives, Lie bracket, and scalar product, put all together, and you obtain a new notion, which is the Levi-Civita connection, the notion of directional derivatives. And this is so important that this formula has a name, and the name is related to the length of the formula. This is called the six-term formula. Okay, so I'm telling you because you can find in a book, in a proof, just use the six-term formula and show the result. It means this. Okay, now theorem. The theorem I was telling you before, it's true only for the Riemannian connection, the Levi-Civita connection. A Riemannian manifold is flat, locally isometric to Rn, if and only if the Levi-Civita connection is, the curvature of the Levi-Civita connection is 0. Okay? Okay. Yeah, we are, let me check time. Okay. Now, chapter 7, section 7. You know, I was telling you, okay, being C infinity linear means that you can put the function and take out just like if the map is linear, but with respect to function. We say that in this case, the map is a tensor. We say that this map is satisfying the tensorial property. We say that in this case, the map is pointwise defined, and so on. All these statements that I asked you, just trust me, okay, just learn it as language. If you want to prove them, this is the section. Okay? Here we explain tensorial means tensor. This is very useful when you delve deep in this topic. And I will skip just to the theorem because we are not doing proof, but I just remark that this is an important part. Where it is? Okay. Okay, this one. Okay, the theorem is this one. As you can see, there is a one-to-one correspondence between bundle maps and F-linear maps, and this is essentially the sentence. A tensorial map is a tensor. Here there is an example with the differential form. I will not go through it, but it's very illuminating in my opinion. So if you're curious, if you reach this chapter and you want to understand, maybe in first reading, just skip the proofs and just take this example just to understand what we are saying. Okay, here there is the notion of the section of the trivial bundle and so on. So we could do this in 15 minutes, but we have only 30 minutes left and I want to finish this lecture because the end is close. And okay, so this chapter is just something related to this. I just want to point out a notation, a terminology that we will not use here, but you can find it and can be scary in first instance. I want to convince you that it is very simple, very natural, nothing to be scared of. Remember that the curvature takes two vectors here, and the result is something that you put a vector into and you obtain another vector. So a result is an endomorphism of the tangent space. Okay, you remember this. So this is an endomorphism. Okay, now if you look at formulas of properties of the curvature, you can show that this map is anti-symmetric. Well, it's not symmetric, the opposite of the symmetric, and meaning this property. And if you remember, this is the property that says when a multilinear map is a form. Remember, a multilinear map, when alternating, this was the word, becomes a two form in this case, because it is a two linear map, a bilinear map, which is alternating. So this is a two form. But remember, a two form usually, the value of a two form on two vector is a number. So normally, a two-form means something with values in R. Okay? Well, this is something alternating, okay? But the value of this is not a number. What it is? It's an endomorphism. An endomorphism of what? Of the tangent bundle. So this is a two-form taking values in this tangent bundle, in this vector bundle, whatever this is, in this object. Well, the notation for this kind of objects is the same that we use for two forms. Remember, omega 2 means the two forms. Usually here you have a manifold, M, so you have the two form on the manifold. This means two forms, of course, on the manifold, implicit in the fact that this is, a vector bundle. Oh, where? Oh, yeah. That this is a vector bundle on the manifold, but you can read this as this is a two form taking values not in the real number, but in endomorphism between tangent vectors. Just a notation for the moment, okay? Just because on some book you can find this kind of language, okay? Just to tell you, this is just a language. I'm just saying this formula. When I say this, I'm just saying two things. That the curvature, when you put x and y here, you obtain an endomorphism, which is not so stratospheric, right? It's quite natural now. And also the fact that if I swap x and y, they change, the sign is changing. Okay? Very, very good. So, Gauss theorem egregium. What is this? Well, it's the fact that the curvature, the Gaussian total curvature, is just an intrinsic invariant of the surface. How can you prove it? Well, you prove that if you take an orthonormal basis, the curvature is just given by this. Why this shows, question, why is this showing that the curvature doesn't depend on the embedding? This expression. Question. Don't be shy. Remember, the Gaussian curvature apparently depends on the embedding because it is the product of two numbers, the principal curvatures, which are defined with respect to the normal direction, okay? And so it depends on the embedding, at least on the normal direction. And I'm saying that if you accept this formula, I'm not asking you to prove this formula. I'm saying, trust me that this formula, it's true, and tell me why, when you know that this formula is true, this shows that the Gaussian curvature is intrinsic, doesn't depend on the embedding. Yes, I heard a microphone switching on. Don't be shy.
Maybe it's some invariant.
Why? Why?
Because it should be the determinant, I guess, right?
I mean, tell me which kind of ingredients are here. What is this minus sign? This is the scalar product, right?
Yes, there is only the scalar product.
There is the scalar product, which is intrinsic. I mean, doesn't depend on the embedding, just the scalar product on the tangent space. And what else there is?
The Riemann, the curvature tensor.
The curvature tensor of the connection on the manifold, not the derivative in the ambient space. So this also is intrinsic, right? You define it using only the the metric with the 6-term formula, if you want. And so you have something, I mean, this formula, the right side depends only on the manifold. There is nothing here suggesting you that there is an embedding involved. Okay? This is the usual way you prove that something doesn't depend from something else. You find the formula expressing that quantity on another quantity which is clearly not depending on the original thing. Okay. Okay, so skip to page 92. Why 92 and this is 93? No. Oh. Okay. These numbers are wrong. Okay. So here we are. Finally, we have section 9. And the question is, what can be done in general dimension? Actually, we already answered several of these questions, okay? Well, general dimension, let's take hypersurfaces in Rn+1. Then we have a shape operator, as usual. And I will go through because we already said almost everything. You see the same formula. The shape operator is defined as the directional derivative. What is changing here? Nothing. Just this directional derivative is in Rn+1. Before it was in R3. So you can think about this section just as a copy of the previous section on R3. Okay, so it's very, very easy. Remember, first property of the shape operator was that it was self-adjoint. Yes, it is self-adjoint. And all the proofs, if you look at them, they are completely the same as in R3. I mean, stating them in a section by its own was just a teaching device. And I think it's very useful because it convinces you that everything can be really seen. Okay, but in every other book, for mathematicians, you would never find something like this. You would find just this section stating everything in the general case, okay? And self-adjoint means real eigenvalues. And real eigenvalues means that you have principal directions and you have these numbers that you can call principal curvatures. And of course, you have a characteristic polynomial of this, characteristic polynomial, this one. Okay, and this characteristic polynomial, you have the first term is the sum of the curvatures, so this is the mean curvature, and this is the determinant, the Gaussian curvature. Actually, this answers Roberto's question. You see, Roberto, the Gaussian curvature is actually up to a sign. I mean, it's not always the product. It's the product or the inverse of the product, depending on the even or odd dimension here. Okay, because the determinant is not this one, is all of this. So we define the curvature with this sign. So this is why the Gaussian curvature is invariant also in odd dimensions. Well, for deep reason, profound reasons that I tried to prepare a slide explaining to you, but they have the reasons are in representation theory of symmetric polynomials and so on. So I wasn't able to find a good argument to explain to you why, but there is a very nice and let's say very easy reason showing that if you take the coefficients of this characteristic polynomial of degree even, they are intrinsic. Okay, because they are essentially combination given by the Riemann tensor. Remember that the Riemann tensor R is a two form. Okay, so it is something of degree 2. Well, it appears that the coefficients of degree 2 here, or degree 2, 4, and 6, and so on, they are combinations of these pieces of degree 2 as forms, as differential forms, in some advanced sense, okay, that I wasn't able to find a way to tell you in a clear way, but then just giving you the qualitative reason why the even dimensional pieces of this characteristic polynomial are invariant, completely intrinsic invariant. For the odd dimensional ones, well, they are not intrinsic, but only for what accounts in the orientation. I mean, once you have chosen the orientation, so the normal direction is given, you cannot switch it anymore, then they are intrinsic also. Okay, so that means that the absolute value of them is intrinsic anyway. Okay. Now we have the Riemannian connection of a hypersurface. What does it mean, this sentence? When I say this sentence, what is the Riemannian connection of a hypersurface? There is a lot in this title, and I will tell you again. I already told you several times, but repetita iuvant, as we say here in the ancient Rome. I'm saying that I have a differentiable manifold of dimension n. This differentiable manifold is embedded in Rn plus 1. This is the meaning of hypersurface, codimension 1. And I'm also saying that this embedding is really an embedding and not an immersion. If you remember, there is a difference between the two words. Embedding means a regular immersion, which is also injective. That means, from another point of view, that this is a subset of Rn plus 1, and this subset is a manifold with the structure induced by the map of before, and this manifold structure is the same manifold structure as the manifold structure induced by Rn plus 1. You see how much I'm saying, and I'm not yet at the Riemannian part. And now I'm saying that, since I'm talking about Riemannian things, that I am in the category of the metric things. So I'm saying that in Rn plus 1, I'm considering the standard metric and the standard connection, the directional derivatives denoted by D from before, okay? And that on this submanifold of Rn plus 1, I'm considering the induced metric. You see, this title is actually 3 pages of notions in this sense. And now I'm asking, okay, with respect to this induced metric, the hypersurface, I know that there is a unique Levi-Civita connection, a unique Riemannian connection. What is this Riemannian connection? Of course, what is this Riemannian connection with respect to the datum that I have of the metric in Rn plus 1? That is, with respect to the Riemannian connection in Rn plus 1, okay? And you already know the answer. You remember? This one. Just the tangential component. Okay, so all this sentence to tell you a very short answer that you should really remember, okay? And remember that the normal component is the shape operator. If contracted with the metric, the normal component is the second fundamental form. Okay, everything is coming back in the same. Okay, and you know what? Actually, I didn't know before teaching this course, but there is also a third fundamental form. Actually, the third fundamental form I knew, but apparently there is also a fourth fundamental form, and so on. It's just the fact that the shape operator is self-adjoint. So if I take L squared and I use the self-adjoint property once, I obtain this. If I use the self-adjoint property once again, I obtain this. Okay, and this defines the third fundamental form of the hypersurface. And you can do the same with L to the power of 3, and you obtain the fourth fundamental form, and so on. Okay, and every time you are just taking a new derivative. Okay, so this is a first derivative because you are taking derivatives. Well, it is a second derivative because the first one is already a tangent vector. Okay, so you already have a derivative and so on. Okay. Well, when we try to write the directional, the Levi-Civita connection in the ambient space with respect to the Levi-Civita connection in the submanifold, you end up with a relation between the two, and this relation is giving just two equations, which are known as the Gauss equation and the Kodazzi-Mainardi equation, which are just expressing the fact that the curvature in the ambient space is 0, but your manifold, of course, has not curvature 0. So when you express the curvature tensor in the ambient space as a tangential part and the normal part, that vector equal to 0, that tensor equal to 0 means that the tangential part is equal to 0, and the tangential part is more or less this one, and the normal part is equal to 0, that is this one. Okay? And guys, we have 11 minutes to finish. I think 3 slides more. Now, you will notice we are page 101, and the book has 379 pages. I tried to squeeze all of them in 4 hours. I wasn't able. And so I decided to synthesize all the rest of the book in 3 slides. Okay, so I will tell you what is missing from my exposition, something very big actually that I have just introduced, but are notions that you should have. Okay, so just focus 10 minutes more. I will just give you a very big overview of what is missing, and I will refer to the chapter, so you can go to the chapter to study. So for the moment, what we have said, let's just read. In studying a Riemannian manifold, we find useful measure the variations of vector fields. Okay, we said in several ways this. And so we need a notion of derivative. Okay? This derivative gives us a unique connection when we ask for compatibility with the metric and zero torsion. And we have this Levi-Civita connection. Now, using the Levi-Civita connection, we have a tensor. This tensor R deserves an highlighting with a different color. The only time I use this color in all my notes, so they show you that this is super important, and in fact I wrote super important and I highlighted the sentence super important, so this should give you the idea that this is super important, because this is exactly the question that we gave at the beginning of the lecture. Okay, and this is the quantity we were looking for, that is the deviation from being Euclidean. And this is the theorem I was referring to. The manifold is locally isometric to the Euclidean space, if and only if the Riemann tensor is 0. But usually checking that the Riemann tensor is 0 is, I mean, it's a very strong assumption, okay? And so you sometimes ask for something less strong. I mean, okay, I don't want to be locally isometric to Rn, but maybe just flat in some direction, just not really flat, but maybe the Riemann tensor is in some sense 0, but not for all the 4 slots and so on. So there is the notion of Ricci curvature. The Ricci curvature is a lowest degree curvature, I mean in terms of rank of the tensor. The Ricci curvature is a tensor of type 2 because you are just taking the Riemann curvature and you are putting vectors in 2 of the 4 slots, in the second and the third. So you leave free the first slot and the last slot, and so you are saturating some indexes, and you obtain a tensor of type 2. Okay, this is an orthonormal basis, so this is the best way to describe the Ricci curvature. This is in some sense the trace of the Riemann curvature. Of course, you have a trace when you have a matrix, so just 2 slots, okay? So when I say the trace, I should tell you with respect to which 2 slots. So this is the trace of the Riemann tensor with respect to the second and the third slot. Okay, making this is just taking the trace, right? And then you have the scalar curvature, where you are taking the trace of the Ricci curvature. That means the total trace, in some sense, of the Riemann curvature. The scalar curvature, as you can guess, is a scalar. So the scalar curvature is the best synthesis you can give of the curvature of a manifold. If you just want just one number, then the number you're looking for is probably the scalar curvature. Okay, how much in terms of one single number is this manifold curved in an intrinsic meaning? Just compute the scalar curvature in that point. And here another realm, another world opens. Question: are the manifold where the scalar curvature in any point is the same number important? These are called the manifold with constant scalar curvature. Yes, they are very important, of course. And then several questions opened in this direction. Okay, let me check. Okay, now think about change completely point of view. Take the Riemannian connection on the manifold and take a orthonormal basis. Okay, as usual, we are always now describing everything by orthonormal basis. So in this orthonormal basis, as I told you, you can take the connection with respect to this vector of this vector and the component with respect to this vector. Okay, this is, by the way, the Christoffel symbol of the connection I was telling you before. But if you take all of this as a function of this argument, then what you obtain is a function on tangent vectors. Well, this function is a form. Okay, it's a linear map on the tangent space. That means a one form. And how many of these one forms do you have? N squared. Each one for each index, right? And so this means that your connection can be described by N squared one forms. And so this means also that you can compute the Riemann curvature using these one forms, and you obtain another 2 form. Remember that the Riemann tensor was alternating in these 2 slots. This means this is a 2 form. So if you call this 2 form capital omega, Well, it appears that the connection one forms and these two forms are connected by this beautiful equation. This equation, of course, this is a theorem. This equation is called the structure equation of the connection. And this relating the curvature with the derivative of the connection. Okay, it is in chapter 11. Don't worry if you don't get the point. Just to tell you that there is so much of the language that we haven't touched. Okay, so the connection is related also to differential form. And maybe you have heard about the Bianchi identity. Well, the Bianchi identity is this cyclic relation between the curvature. It's cyclic in the sense that x, y, z, x, y, z, x, y, z. Okay, just put x, you start with x in different place. Now, and we are over, please give me 2 minutes more. Well, think about this. Take a curve in the manifold. Do you have a curve, right? So you have a tangent vector to the curve. This is a tangent vector, but it's special because it is related to the curve. Okay? And you can take the derivative in this direction with respect to the variable of the parameter of the curve. So you can ask for curves which has the second derivative in some sense equal to 0. Because remember, in Rn, if you want to characterize a straight line, what can you do? You take the first derivative, the tangent vector, which is the first coefficient, and then you take again the derivative and you call the curve a line if the second derivative is 0, right? So, idea. I want to define the straight lines in a general manifold. I can do the same. I take the tangent vector to a curve. I take the derivative, that is the derivative that I have because I have the Riemannian connection, okay? And I use as the direction of, I'm taking the derivative on exactly the tangent vector. So I'm taking the derivative of the curve by itself. And if this derivative is 0, I call this curve very special. It is self-parallel in some sense, and I call this a straight line, which is no more straight in the straight sense, because we have no embedding in Rm. We're just an abstract manifold. So this is a way to define what is the straight line on a manifold. That means this is a way to define the shortest path, because theorem, a straight line in this sense, is also the shortest path in the metric sense. And by the way, we should define the metric as a distance on the manifold. At the moment, we have only length of tangent vectors, okay? And we use integrals, of course, to define the distance on the manifold. So you see how many things. Well, this is the concept known, the notion known as geodesic. A curve which is parallel in this sense, that is, its second derivative is 0, is called a geodesic, chapter 14. Okay? And derivative along curves gives finally the notion of a parallel transport. Because now I was taking the derivative of the tangent vector to the curve, right? But I can take the derivative of any vector along the curve. And so I can transport a vector from a point to another point. This is the notion, the parallel transport, that in the manifold is no more parallel. I mean, the notion, the visual notion of to be parallel in Rn is no more possible in the manifold. This is the way we give a meaning to the notion of parallel. Okay? And the parallel transport is given in chapter 14, and I end up showing you something very surprising, which gives rise to a completely new notion that is the holonomy of the Riemannian manifold. And for this, I need to show you just a picture that is this one, and then we are finished. So I just need to explain you this picture. What is this picture? So this is a tangent, this is a sphere, okay, in R3. Nothing fancy, nothing special, just a sphere. Well, take a vector, tangent vector here. And now we want to transport this tangent vector parallel along this curve. Okay, these are three curves. Okay, it's a single curve actually going back to the original place. Well, transport it in a parallel way. Okay, remember that the Levi-Civita connection on the sphere is just the tangent component of the Levi-Civita connection in the space. So parallel transport means that you take this vector, transport parallel in another point in R3, and then you of course obtain something which is no more tangent to the sphere, and then you project on the sphere. And if you do this, you obtain this, this, and this. When you arrive here, the vector is this, right? So we start taking it parallel to the sphere. And so we are here, still tangent, okay? Everything is tangent to the sphere. Okay? Oh, what is that? Okay. Okay, we are here, and then we go back. We are here, we are here, we are here. You are back. What's happened? What?
The two vectors are no more the same.
And no more the same. Is this? I mean, for me, it's unexpected. I'm transporting parallel. Try to do this in Rn. I mean, if you transport parallel, you always end up with the same. So parallel transport on a Riemannian manifold, when you go back to the space, is giving you something different. And you know why? Because the curvature is not zero. So you have a map on this tangent space, an endomorphism, right? That take a tangent vector, transport it along a path, going back here, and obtain another tangent vector. Okay? And this map depends, of course, on the path you are choosing, but this map is a transformation of the tangent space. So could be the tangent space, let's say for the moment, it's just R2. So this map can be a general map in R2, but could be an orthogonal map in R2. So in O2, I'm talking about the matrices, okay? Could be a special orthogonal map, meaning orthogonal with determinant equal to 1. Could be also something in some subgroup of SO2. Well, it appears that the group this map is taking values into, that means, for instance, this map is taking values in SO2, means a special property of the manifold. In particular, if there is a metric, then the map is orthogonal. And so it's taking values in SO2, if there is a metric and there is an orientation. This group that this map is taking all these values into is called the holonomy group of the connection. So now we have a new notion. When we have a connection, you see no metric involved here, just the connection. The connection is giving you a property which is called the group, the holonomy group of the manifold. And this is an invariant of the manifold with the connection. So, just to give you the idea, this is just drafted in the chapter 14. This could be another single book. It is a very active and very beautiful topic of research, just like everything else I was talking about. And I'm very happy, I'm sure you are very happy to read that this is the end, but it is the end, I mean, for me, and it's the end with a question mark, because actually we are going to have the thrilling finale by Daniele, that will be your teacher next week, and we'll try to give just a sketch of another very important part in differential geometry. You see, at the beginning we have just done the manifold structure. Today we have done manifold structure plus a metric, okay? Next week we will do manifold structure plus another kind of structure, which is similar to the complex structure, the complex multiplication in complex numbers. What is complex multiplication? When you multiply by I in complex numbers, what is the property that you think about? Define I, the multiplication by I, what it is?
Rotation.
Rotation, and if you apply the rotation twice, what happens?
You just change direction.
Change direction. So I would just synthesize the complex structure just as an operator, an endomorphism, which is square to minus the identity. Okay? Well, welcome to the realm of complex structures. A manifold with an endomorphism of the tangent space satisfying this trivial property, which is trivial, I mean, just I square equal to minus the identity, gives you such a powerful structure on the manifold that you have no idea, which is called the complex structure. And assuming some much stronger condition, the integrability of this complex structure, your manifold, which was originally diffeomorphic to Rn, is actually diffeomorphic to Cn. It is a complex manifold. You understand what this means? It means that you can make complex calculus, complex analysis, which you know it is very, very powerful. Okay? So this structure is very important when it is integrable, and Daniele will talk about this, and I guess also about symplectic manifold. I don't want to spoiler a lot, also because you are probably cursing me because I'm 10 minutes later. Okay, I'm over. Thank you very much.
Thank you, Maurizio, a lot for all your precious insights on this topic. Maybe I have just one question for Daniele or Maurizio as well.
Okay. Yeah.
I don't know if you're here, Daniele. Great.
Sorry, yes, I am.
Great. Are you following the same teaching approach as we did so far? I mean, are you going to following a book or this book, one of these books, or not? Because I cannot figure out if
not exactly.
Topic, okay.
So
well, probably Daniele want to say that he cannot be so awesome as I was, exactly. But he will do his best.
I will share with you a test book in the next days, where more or less there are several things that I will talk about, and also some further hints. But I will try to do like a survey, and so it's not so easy to find a test book with all the stuff. So I will complement it with some notes.
Clear. Yeah, okay. I'm just asking in order to be prepared for your lecture.
I will share with you tomorrow or on Wednesday. Okay.
Perfect. I know that some of you have some difficulties in finding the files that we are uploading so far. Actually, I guess the problem is that when you do a login in Microsoft Teams, you should use eventually your guest account. So maybe you have been invited with the same email as your institutional one, but since the invitation is coming from another institution, there is an option to log in as a guest instead of your institutional login. And in any case, for those of you who have some troubles in getting the material we are uploading on the Teams webpage, just send me an email, so to Roberto Alessi, and I'll send you maybe directly a link or instruction how to do this. And meanwhile, I know that Maurizio is also uploading the videos to the recordings of the lectures on YouTube directly. So it will be easy for me, for instance, to send you the annotated PDFs and the material, and for the videos, if you have difficulties in getting them from OneDrive or from Teams, actually, you can get them from YouTube directly. Okay, I don't know if there are any questions and remarks from other ones.
Yeah, I have a question for Maurizio. Can you hear me?
Yes, I can.
Okay, good. So you introduced the connection, and from the connection you derived, you said what parallel transport means. In some physical problems, maybe it would be nicer to go the way around to define. Maybe we know what parallel transport means. Is it possible to go back and to define?
Yes, in some textbook, this is the approach used.
And do you have a reference?
I can find a reference for you.
Okay, thank you very much.
Because you want this definition. I mean, in this book, there is the parallel transport, but you want a reference just taking the parallel.
Around.
Okay, okay. Yes, yes, I think I can find you. I'm not sure what I'm saying, but I think this could be the original approach of the definition of a connection, starting from parallel transport.
The notion of connection on principal bundle is more or less in the spirit, no? So
yes,
if you look at the
parallel transport, yes, but of course he's asking me for a reference. I will never give him a reference on principal bundles.
No, but there is a chapter in the book for this reason.
Okay, okay.
I'm asking for a very short reference.
Okay, okay, I will look for it. Yes, this is another language. The language of principal bundles is a very powerful one. And just to warn you, if you try to read some textbook and they start with principal bundles and connections on principal bundles, don't be too much scared. I mean, it's a very powerful language and useful language. Maybe now you can understand it after this.
Thank you very much.
Welcome.